start. Okay, we are here the 21st, the first day of summer, right? And we finished electromagnetic waves last time, so now we are going to do chapter 34. This book called Images. And then at 12 noon, you're going to do the first lab. You already have your group set up, and tomorrow is the exam, the first exam. Let's review that again. Just repeating what I'm saying, what I have already said before. Let's see here, this one here. Yeah. For the exam. Okay, with no exception, chapters 15 and 16. We're covering only those three sections here in chapter 17, and for now, right? And those three sessions for chapter 33, that's for the exam. But we cover everything in chapter 33, right? So we leave the rest, the other sections for the next exam. And today, what we're gonna do today, we're gonna finish chapter 33 and start chapter 34. Chapter 33 is going, what's missing? Chapter 33 is 33.7. Okay, so what we did here, we did 33.1, 2, and 3 first, right? Then you did reflection and refraction. We momentarily skipped 34, total internal reflection. Then we came back to polarization. Now we're going to finish polarization by reflection. That's the last topic. So chapter 33.7, polarization by reflection. So in general, so let's write it down here, just a quick summary, right? In general, light is randomly polarized. And what does it mean, randomly polarized? The electric field vectors, right? Points in a very possible direction. Okay, polarizers are devices that manage to filter out the electric field in all possible directions but one. Then the idea of linearly polarized light. Okay. And the illustration that you saw was, oh, not this one here. here you go. The illustration that you saw for the randomly polarized light is this one here. Yeah? Notice that in order to understand what's happening here, you must understand the electromagnetic waves, right? So this representation here is just showing to you that electric field is going up and down, up and down, up and down, right? As the light propagates. But it's not just in the vertical direction, it's also in the horizontal direction and in this 45-degree angle direction as well. Randomly polarized light is best represented just according to your book, right? It's a very good representation just by this cross of arrows. Even though in reality you have a bunch of arrows filling all this space here. But that's the representation of randomly polarized light. And your polarizer managed to eliminate every possible electric field, but one along a given direction. So if you have a polarizer that filters out the light in the y direction, so let's say only this component here of the electric field is going to remain. And when I mean only this component here is going to remain, it means this will remain and all the projections of those electric fields along the y-axis. This one there won't pass because it's 90 degrees with respect to the polarizer, right? But everything else that's filling this space here, everything else that has a projection along the y-axis is going to pass some of it, not all of it. And that's that's an important piece of information that you have to know. Points, the electric field vectors, points. Notice that I put vectors, right? Pointing every possible direction. That is, by the way, that is perpendicular to the propagation of the light, okay? Polarizers are devices that filter out the electric field in all possible directions but one. Then the ideal linearly polarized light. Okay, that's polarization. Here you go. This is polarization by transmission, or even better, polarization by refraction / refraction. Then I'm going to put it right in here. That's what we covered. Polarization by transmission or polarization by refraction, right? Summary. It's also possible. It is also possible to polarize light by using reflection. It's also possible to do that. And that's what 33.7 is all about. Polarize light by reflection. And there is a little, neat piece of information that I want you to memorize. We are not going to prove that mathematically. In order to prove that mathematically, we need higher levels of physics. Okay, and let me illustrate. What polarization by reflection is all about. Okay, so let me just remind you the polarization by transmission right before we go. Let's see, here you go. Polarization by transmission, right? The polarizer, the light passes through the polarizer and it becomes polarized. Okay, now that would be by transmission or refraction because we have a very thin material that can do that. So light in a way is refracted, right? Now, what about polarization by reflection? Polarization by reflection. It's possible to have polarization by reflection. It's also interesting. Okay. For some reason, that's okay. Yeah, for some reason it's not. This box here is not. It's not. Okay, now I got it. Good. Center justified. Okay, so let me explain to you exactly happens when you have any angle of incidence. Here you go. Here's slide. Oh, I did all over again. Okay, I mixed that up. Oh, wait a minute. Yeah, I mixed this one up. That's the one that I mixed up. Okay, here you go. Representation of light incident at the interface of media 1 and 2. See, someone left a message just to refresh. When is angle of incidence equal to the angle of reflection? All the time. When angle of incidence is angle of incidence is always equal to the angle of reflection. Okay, so here we have the angle of incidence, right? And here we have the angle of reflection. Notice that those angles are the same. Always. It doesn't matter if it's a mirror, it doesn't matter if it's a glass. Okay, so let's say we have a glass surface here. Water, okay? Always equal to the angle of reflection. All you need to know is but don't forget that the angle of incidence is equal to angle of reflection with respect to the normal to the surface, right? If you find the normal to the surface, the angle of incidence is going to be equal to the angle of reflection. And it doesn't have to be this nice polished surface, okay? It can be a rugged surface as well with all sorts of kinks and and bends. All you have to do is to find the normal to the surface in that specific position. It's still gonna be angle of reflection, is still gonna be equal to the angle of angle of incidence. Okay, so here you go. And we have this light here that's randomly polarized. That's why I indicate this vector that you see here. I want to make it look nicer. Okay. And not only we have the electric field parallel to the plane of incidence. This is the plane of incidence, the plane of my screen, right? Or let's say the plane of my paper if you draw it. And let's see how I'm gonna I want to make a little bit larger. Nope, that's not what I want. Yeah, I want to do like that. Let's see. I want to increase a little bit more. Yeah, that's what this big dot is all about. This big dot is the direction of the electric field as well. Electric field oscillating in the plane of incidence, and the electric field also oscillating perpendicular to the plane of incidence, okay? When you get any angle of incidence, what do we observe? I'm not gonna prove that, okay? I'm not gonna prove that, I'm gonna just tell you what we observe. The proof must come with more advanced equations. So the light is incident here and reflected, right? Incident and reflected. Make it look nicer as well. More students coming in. Okay, view these lines. Make it look nicer. So I'm going to put it back. Yeah, here you go. Now this go around here. Okay. And now I have, nope, not here. Let's see. Yeah, it is here, but then I have to extend this little arc like that and contract this one. And I'm going to do something else. I'm going to make it black and thicker. I usually find that the thicker arc looks nicer than those thin arcs that come with PowerPoint. And that's the angle of incidence. The default, okay? And then we have the angle of reflection as well. The angle of reflection is going to be a little bit, the square of the angle of reflection is going to be a little bit larger. Oh. Go down. And go. So it doesn't overlap with the other. One more student joining us. Okay. Oh, not this one here. Okay. So what do we observe? We observe that when there is reflection, this amplitude here parallel to the plane of incidence decreases. Okay. So but decreases with respect to the electric field that's perpendicular. Both decrease, both the this component and this component decreases inside because you're going to have some of the light going to the medium and some of the light reflected to the medium. Okay, both of them are going to decrease. However, the component parallel is going to decrease more than the component perpendicular to the plane. Okay, electric field component perpendicular, electric field component parallel, and I'm going to get this one there as well. But then there, okay. So let's write it down before we go to the next slide. Reflection, okay. Looking at the drawing, at the illustration, right? We have the following experimental result that we obtain. This experimental result can be proven with more advanced physics concepts, okay? So I'm not gonna prove here. For this reason, I'm not gonna prove what happens. For this reason, I'm not gonna prove that. I'm not going to prove that. So what do we observe, okay? Initially, light is, looking at the illustration, okay? Look at the illustration. We have a randomly, let's see, we have a randomly polarized light incident at the interface of a glass, okay? Let's say. What is observed, what is described, you know, is what is observed experimentally. It can also be proven that, okay, this experimental result can also be proven theoretically. With more advanced physics concepts. For this reason, I'm not going to prove that. So I need you to remember that. Initially, light is randomly polarized. Not light, let's see. Initially, the light's electric field is randomly polarized. With components parallel to the plane of incidence, with components parallel and perpendicular to the plane of incidence. Okay. Once this light is incident at the glass surface, okay, some of the light reflects and some of the light refracts. So the reflected light in general, okay, in general, the reflected light has both polarizations in general, the reflected and refracted light. Let's put the different way. Okay, the refracted light, let's do it this way. The refracted light has polarizations along both directions, okay? Although with a smaller electric field, right? But you must have conservation of energy. And the refracted light always will have polarizations along both directions, although there's a smaller electric field. As for the, okay, so I'm gonna put, to simplify here, item A, right? The refracted light always will have polarizations along both directions, although with a smaller electric field. As for the reflected light, in general, the polarization of the electric field parallel to the plane of incidence will be larger. Okay. So initially, because the light is randomly polarized, okay, suppose the light polarized parallel to the plane of incidence perpendicular to it, is going to have same amplitudes. After reflection, in general, the polarization of the electric field parallel to the plane of the incidence will be polarization of the electric field perpendicular, not parallel, perpendicular, and it would be, the relative, right? The relative component, of the E field perpendicular to the plane of incidence will be larger than the other, which is parallel. Okay. And I'm going to illustrate that for you. One more student coming in. It's not illustrated here, okay? The only thing that I can illustrate here is the fact that the amplitude of this component parallel to the plane is larger than each of those amplitudes here. But you must have conservation of energy, right? The intensity of this one plus the intensity of this one must be equal to the intensity of this one. But what I cannot illustrate here in this picture is that the relative amplitude of this component here is smaller than the component that's perpendicular, right? So that's what we have in general. That's what we have in general. That's what happens in general. That's what happens in general. Okay? However, there is a specific angle that we call the Brewster angle, the reflected light will be polarized will be linearly polarized, right? Will be linearly polarized. And this polarization will be, this polarization will be at a direction perpendicular to the plane of incidence. Okay. Okay, and how do you illustrate that? This is illustrated right here in this next picture. And okay, so if we go ahead and make this light incident at a specific angle that we call the Brewster angle, light will be polarized only in this direction perpendicular to the plane of incidence. Okay, can you remember that? You must have a specific angle. You must have a specific angle for that. The question now that you have to ask yourself, what is this angle? Okay, what is this angle? And now I'm going to put here, good morning, my opponent. Yes. Okay, so here we go. Now I'm going to put a Brewster angle here. I'm going to put just the letter B. to indicate Brewster. Okay. Don't forget the angle of incidence is supposed to be the same as the angle of reflection. The angle of reflection was supposed to be angle of incidence. Okay. So under this condition, okay, there will be polarization only perpendicular. There will be polarized light only perpendicular to the plane of incidence under this condition. Okay. And what this condition look like? That's the next question you gotta ask yourself. Okay. That's something you have to memorize. You cannot prove that mathematically. And here you go. Here's the angle of refraction. Yeah, very small, right? Very small angle of refraction. And I'm going to call that theta of refraction. This will be polarized, but not the refracted light ray, okay? And that is illustrated in your book as well. Of course, they have a better, they have a better illustration there. Let's see, 33 right in here. Okay, so here they just go ahead and show the polarized light. Okay, here the electric field oscillating back and forth in this plane and oscillating back and forth on the plane perpendicular to this page, right? But they oriented also in a different direction, right? Some of the light is refracted, some of the light is reflected. And when the light is reflected at this specific angle, the reflected light will be polarized at the direction perpendicular to the plane of propagation. Plane of propagation, okay? So what's the condition for that? And don't forget, this here is angle of refraction. I'm gonna put R in there. The condition that you have to know, it's not difficult to memorize, okay? Is that this angle here, Brewster angle, plus the angle of refraction are going to be equal to 90 degrees. So when the incident light is incident at a, when the incident light plus the refracted light is equal to 90 degrees, we have polarized polarization due to reflection, right? Totally polarized. Here in this case, light is totally polarized on reflection. Light totally polarized. Here is totally polarized as well when reflected. When you have the Brewster angle, right? So let's write it down. Notes. However, at a specific angle that we call the Brewster angle, the reflected light will be linearly polarized, and this polarization will be perpendicular to the plane of incidence. Okay. The condition for this angle is, let's write it down. Is this one here. So the angle, when the angle of incidence is equal to the Brewster angle, we have polarization under reflection. Okay, that's the condition. So, using Snell's law, right? Using Snell's law, you can find what this angle will be for two different indices of refraction. Okay? So let's get here's Snell's law. Okay? Theta 2 is the theta of refraction, right? So we are going to rewrite theta of refraction in terms of the Brewster angle. And let's not forget, theta 2 is the angle of refraction. And theta 1 is the Brewster angle. I'm going to put it here, 1 minus theta 1, right? Theta 1 is the angle of incidence. So let's go ahead, put it here. Theta 1 is going to be the Brewster angle. Theta 2 is going to be 90 minus the Brewster angle. And that's a sine. 90 minus sine of 90 minus the angle is going to be the cosine of the angle. So that's the relation, that's the condition for the Brewster angle. Right? If we pass this cosine of theta Brewster and then one to the other side, we take this one out like that. We get the tangent of the Brewster angle, tangent, n2 over n1. Okay, so if this condition is satisfied, if this condition is satisfied, then the polarized light then the reflected light will be polarized. Okay. Let's do an example. Right? Consider a light, consider unpolarized light in air being incident at the interface let's say, at a piece of glass, right? A piece of glass, refractive index 1.5. What is the Brewster angle? A piece of glass of the Brewster angle, right? That's straightforward. All you gotta do is apply the formula in a straightforward fashion, right? That's gonna be 1.5 divided by 1, which is 1.5. And then you have to take the inverse tangent of this value. Arc tangent of 1.5. And that's what the Brewster angle will be for those two pairs of media. Okay, and let's see how much that is. I shouldn't take attendance, right? So let's go here. A tangent 1.5. And let's not forget, I want that in degrees. I'm getting 56 degrees, 56.3 degrees. Okay. So refractive index 1, refractive index 1.5. Right? If this angle here is 56.3, right? It's 56.31, let's say, then the light, the reflected light will be polarized. $844. One more student. Don't forget tomorrow is the exam, right? Let's take a look here, the book. Here you go. You can do for all sorts of situations, right? Let's do one more. I want to do one more, okay? So suppose, okay, here you go. Brewster angle, let's see, checkpoint. Yeah, he doesn't have an example, right? Unfortunately, yeah. Okay. I want you to do the following example on your own. Okay. Invert the situation. Invert the situation. Okay. Find the Brewster angle for N1 equal to 1.5 and N2 equal to 1. And N2 equal to 1. Okay, I want you to do that on your own. And in 15 minutes, I'm going to ask you what you got there, okay? And then we do that together. Now, 15 minutes is too much, right? Like 10 minutes. Take 10 minutes to do that. And then I will return in 10 minutes, see how you're doing, okay? I'll be back soon. Take time, take time to do that. Find the Brewster angle for N1 equal to 1.5 and 2 equal to 1. And I will be back shortly. Okay, how are you doing there? Should be able to do that quickly, right? This one is 56.3 degrees. 56.3 degrees, like that. That's from air to glass. What about from glass to air? What if, right? Light is coming from the glass. Is propagating from the glass towards the air. Okay. What would be the Brewster angle? What would be the Brewster angle? Right. There you go. In other words, right? Find the Brewster angle for n1 equal to 1.5 and 2 equal to 1. Solution 8:49. 5 more minutes. While you do that, I'm going to take attendance. Roster. Eugene Choi. I don't see Eugene there. Ashley Shu. I see Ashley Tai, but not Ashley Shu. Zakir. No, oh man. All those students are not showing up. Amy. Amy is here, yeah. Right? Thank you, Amy. Andy. Andy he. Let's see. Okay, thank you, Andy. Another one is Alex Hernandez. Alex Hernandez. I'll be back. Yeah, that's right. That's a Terminator reference, right? I'll be back. Okay. Emily. Oh, before we move forward, right? I mean, are you having any problems doing this example?
No, I'm still working on it.
You're working on that? Okay, good. Need any help?
No.
Okay. What about Andy? Are you able to do that, Andy? Okay, good. Next, Emily. Emily is not here, right? Okay, Emily is not here. Next, Sartak. Yeah. Are you working on the problem, Sartak, on the example? Okay. Any questions about that? Okay. Stephanie here. I don't see Stephanie. Okay, so one more. Zaid. Where is Zaid? I don't see Zaid. Alisa.
Here.
Okay. So do you have any problems, Alisa?
Not right now.
Okay, good. Karthika? Karthika, right?
I'm here and I'm working on the example.
Okay. So you're working on the example. Good. Mary?
I'm here.
Okay, any questions about this example, Mary?
No.
Okay, Raymond? Looks like Raymond already did, right? Raymond? Okay, so one more. Ashley, Ty?
Not here.
Okay. Any questions about this example, Ashley?
Nope, I'm good.
Okay. Kyriakos? I don't see Kyriakos here. Alexis Valley?
Here.
Okay, any questions about this example, Alexis?
Not at the moment, thank you.
Okay. Joshua?
I'm here.
Good. Any questions about this example, Joshua?
No.
No. Next is Basilio. Let's see, Basilio, is he
No,
there?
I'm here.
Oh, you're there? Okay, good. Any questions about this example, Basilio?
Thank you.
Any questions?
Oh, no, thank you. No,
Okay.
thank you.
Okay. So Daniela, I don't see Daniela, right? And Sydney,
Yes, I'm here.
any questions about the example, Sydney?
No, not at the moment.
Okay. And Sumana? Hello, Sumana, are you there? Okay, Sumana is not answering. I'm gonna put this star here for now. And how many students? 12, 13 with Sumana. Yeah, good. Those numbers match. 853. Let's do that together now. It's straightforward type of problem, right? You want to use the same formulas that I put it here, but instead of taking the arctangent of 1.5, I'm going to take the arctangent of 1 divided by 1.5. That's all, right? And I'm getting 33.7 degrees. So, okay. And now we're done with this chapter. Done with chapter 33. Let's see. One divided by 1.5, 33.7 degrees, right? Done with chapter 33. Let's start with chapter 34 now. Chapter 34, images. Images, okay. Yeah, that's right. Yeah, all the time. Yeah, we take the arc sign for the Snell's law, right? So just keep in mind, let me write that down here, okay? This Brewster's so-called law, right? It's not exactly a law. Brewster's law is a special case of Snell's law. That's what Brewster's law is all about, okay? Brewster's law is a special case of Snell's law, right? That's what it's all about. For any other angles, we find the arc sign, right? But for the Brewster angle, the arc sign coincides, let's see, coincides with the arc tangent. Okay? That's why it's a special case. It's a special case for what? A special case for this Snell's law under this condition, right? Okay, that's the special condition that reduces to that equation with the arc tangent. Because of this condition, the arc sign reduces to arc tangent. Okay, changes to arc tangent. Special case. Yeah. Now we can start talking about images and spherical mirrors. and lenses. Okay, we start with spherical mirrors. No, wait a minute. First is planar mirrors. We already did planar mirrors, right? Images. But let's do it again. Planar mirrors and spherical length, and it's planar mirrors, spherical mirrors, and spherical lenses. And it's, in a way, we already did the planar mirrors, but I'm gonna do that again very quickly. Planar mirrors, and image formation. Like that. In this chapter, you have to learn, in this chapter, you have to learn, you will learn the technique to find the image of objects, how the image, you learn a technique to find the image of objects. Okay, that's what it is. And like we already did that for a planar mirror, but I'm gonna do it again. Planar mirror, but we're going to do that again. Don't forget, this is geometric optics, because it's geometric. It's a very good name. Okay, the series that we are studying is called geometric optics, and it's called geometric optics because we use geometry to find the images of objects. So it's a very good name. It's reflection, okay? Reflection and mirrors, okay? So we have this point source, this source of light, and emit lights all over the place, right? In every direction. And let's start with the planar mirror, just like I mentioned before. Here's the mirror, and I don't want grid lines anymore. Grid lines look so ugly. Planar mirror. Here's the source. This source is emitting light in every possible direction, right? And here is just one possible direction that the source is emitting light. Just one possible of the directions. And according to the law of reflection, right, the angle of incidence is equal to the angle of reflection. I'm going to specifically state here reflection with L. There is no refraction because this surface is a mirror. It reflects 100% of the light. Okay. And if I want to find out, the idea here is to find out the image of this object, where the image is formed. And we're going to use arguments of geometry to find that out. In order to find that image, we need at least a second light ray. Remember, I told you this light source is emitting light all over the place in every possible direction, unless it's a laser, right? Unless it's a collimate light source like a laser that emits light in just one direction. But most objects emit light in every possible direction. So here you go, we have the second light ray in order to find the image. What we have to do? we have to extend the reflected light ray behind the mirror. Here too, we have to extend the reflected light ray behind the mirror. But before we do that, let's consider a third light ray. You don't need a third light ray to find the position of the image. All we need is 2 light rays. But let's get the third one here. Right? And now we go ahead and extend the light ray behind each reflection. I don't like this guy. This guy is supposed to pass through here. Okay, and I'm not gonna put a solid line. I'm gonna put I put this one as a solid line, but the extended line is gonna be dashed. Okay, and won't have any arrows whatsoever. Let's see, maybe I can get away with the arrow. Yeah, I can get away with this arrow. Okay, so slightly off, right? As before. Let's take a look at the grid lines here. Let's see if those lines are straight or not. No, they're not straight. Okay. That's what the grid line is all about. If I want to do this drawing in a very realistic way, I gotta make sure that all my lines are straight, right? So this line here is not straight at all. Okay, like that. So I did my first dashed line. Now I'm gonna do my second dashed line. And that second dashed line is gonna be red color. And I'm going to contract this red line. It's not completely aligned. Let's see if we can do better than that. Okay, here you go. And now if everything is right, if you have the angle correct, placed correctly, right? The third reflected line will align with the other two. And will be somewhere around here. I'm going to contract that here. And then I will make it dashed. Okay, let's see if it's the right place or not. A little longer than that. Nope. Let's see, I'm gonna make it longer. Those grid lines are pretty good to ensure that everything. Okay. So I want you to practice there in the paper or even in your computer screen. Yeah, it looks like my dot. See, my dot is not exactly in the right place. Okay, but that's because the angles here are not correct. Okay, so this dot is supposed to be somewhere a little bit lower. And if it's not in the proper place, that's because I didn't get the angle properly. Okay, so here you go, like that. I used to do that in the paper when we didn't have computers. I'll get the so is the reflected image always along the same line? Yeah. Unless the mirror is at an angle. Okay. This mirror here is not at an angle, it's at 90 degrees. If the mirror is at an angle, then it's gonna be different. Okay, Raymond? It's not always, right? It's not always. Let's see. Ay. Let's get this thing here. Let's see. I got it now. What's that? Ah, this one here. Oh, let's do it again. Okay, just this one. Maybe somewhere around here. Okay, and then I'm just adjusting for what it's supposed to be. In order to do very realistic and in the proper way, you have to ensure that the angle of incidence is equal to the angle of reflection. Now, PowerPoint allows you to do that, but I'm not doing that because it would be too much work. It was going to take too long to do that. So, okay. So that's the technique that you gotta use. Okay. You gotta extend the reflected light, the light ray, the reflected light ray. Okay. So let's write it down. Planar mirrors. Okay. To determine the position of an image with respect to the planar mirror, you must get at least 2 light rays. 2 light rays. You must use, right? At least 2 reflected light rays that comes from the source. That comes from the source. You must use at least not 2 reflected, but 2 incident light rays that comes from the source, okay? By using the law again, law, right, of reflection, between quotes. By using the law of reflection, you determine the reflected light ray, and then extend it. You determine by using the law of reflection, you determine the reflected light rays, right? Because it is at least 2, and extend them behind the mirror. The point of intersection of these extended light rays is the position of the image. Okay. And we are going to use a similar technique for spherical mirrors and lenses. And let's not forget it's spherical mirrors. The mirrors are spherical. They're much easier to predict than other types of mirrors. Spherical mirrors and lenses are not the best type of mirrors and lenses, but they're still very useful. They're easier to manufacture, and they produce a good image up to a certain point, right? Past this point, then you have to start using parabolic mirrors, hyperbolic mirrors, and so on. So what we're doing here in this course is an approximation of the best type of mirror and lenses that you're going to find out there in real life, okay? And looks like we have one more student here. I'll have to, this one here. Let's see, who came right now? Alex Hernandez, are you there?
Yes.
Okay, so we go. Anybody else? 13, let's see, we have 15. Looks like we have one more student here. Emily is here. No. Stephanie is here. I don't see Stephanie. Zaid, no. Kyriakos. I don't see Kyriakos. Oh, wait a minute. There is this student here. Sumana, are you there, Sumana? Sumana is still not answering. Okay, I'll keep my starting there. And now we can have our break. 9:15, 1 hour and 15 minutes. Notes, not this one here. Break from 9:15 a.m. to 9:30 a.m. Okay. Okay, so for the case of Raymond, right? Raymond, you might want to, just as an exercise, since you asked about whether the image is always in the same line, do the case for a mirror that has, an angle there. Do the case for a mirror and an object using the same technique that I used, okay? But for a mirror that has an angle group like that. It should lie in the same line, provided the line is traced perpendicular to the mirror, okay? So here you go. This light is gonna be like that, right? And then there will be another light that will be reflected, okay? And then there will be an image formed, right? If you draw the line perpendicular to the mirror, yes, it's gonna be the same line, provided the line is perpendicular to the mirror. Yeah, still equal to the angle of incidence. That's right. It's still equal to the angle of incidence. Think about that. This mirror here, this system that you see here, group, right? Let's see if I can do that. Can be rotated, right? Back like that to look just like in the same way that we did before, right? This problem is no different than the other. This problem is no different. It's just a different referential. It's just a different referential, right? Okay. Yeah, thank you. Okay, so let's go for our break. And from 9:15 to now it's 16, right? Let's put 16. One more minute here for us. And I see you in 15 minutes. I'm back here. And now we can start with the spherical mirrors now. Spherical mirrors. This is a very simple theory, very intuitive. It's not difficult to understand. It's not difficult to grasp it. Okay, and okay, so that's for the planar mirror, right? This one is planar mirrors. You go, planar mirrors. I'll leave this one here. And now I'm going to start with spherical mirrors. This. And now it's spherical mirrors. Grid lines. Okay. So it's a very useful type of spherical mirrors, a very useful type of mirrors. It's not the ideal type of mirror, but it's useful. Okay. So you can write like that. The spherical mirrors are not the ideal type of mirrors in terms of image formation, right? Are not the ideal type of mirrors in terms of image formation. But they are still very useful to a first approximation. Okay, to a first approximation. An ideal type of mirror would be a parabolic mirror. An ideal type of mirror would be a parabolic mirror, not a spherical one. Or let's say paraboloid mirror, right? Should be paraboloid mirror. But there are more, but these would be paraboloid mirrors. But these are more difficult to manufacture. That's why we stick with spherical mirrors. So how do we illustrate a mirror, a spherical mirror? They're called spherical because they have spherical symmetry, okay? So we go ahead, we get a sphere of radius r that we call radius of curvature, right? And we slice it, one hub, right? And then we get this section of the sphere will be the surface of our spherical mirror. So here you go. We make that section reflective, and we have our spherical mirror. That's how we do it. The manufacturing, details is not this one that you're seeing, but it's just for you to visualize what a spherical mirror looks like. Okay, they are called spherical because they are derived from a sphere. And this surface here is just a section of a sphere, the surface that you see. Okay, these mirrors are called spherical mirrors because they make up a section of a sphere. They are made up from a section of a sphere. Right here you go. Don't forget that this mirror has a center of curvature that coincides with the center of the sphere, right? That's what C is all about. That's what C is all about. A center of curvature equal to R. Can be 1 meter, 1.5 meters, 2 meters, can be 50 centimeters, and so on. Okay, the larger the center of curvature of the mirror, the better its behavior, its image formation, okay? Now what we have tangents to this surface, right? Tangent plane that's tangent to the spherical surface. And this tangent plane dictates the direction of the light ray that's incident in the mirror, on the mirror. Okay, very important, any light ray that passes through the center of curvature of the mirror, any, okay? Whether it's this direction or in the other, is going to reflect back towards the center of curvature. It's going to reflect back towards the center of curvature, okay? Any mirror, any light ray. But it must pass through the center of curvature. Light rays, because one put light rays, right? Passing through the center of curvature, reflect back on itself. Why is that? There's a reason for that, right? There's a reason. The reason is that we are measuring the angle of incidence with respect to the normal of the mirror. The normal is perpendicular to a plane that's tangent to that point. So if it's passing through the center of curvature of the mirror, automatically this light ray is going to be perpendicular to this plane that is perpendicular, that is tangent to the surface of the mirror, okay? Tangent to the spherical surface. That's one important piece of information. You're going to need that to build your images, okay? For, let's say, these mirrors are called spherical because they are made up from a section of a sphere. Consider a sphere, right, of radius r with a center of curvature located at point C, right? Any light ray passing through the center of curvature will reflect on itself, okay? Even better, any light ray passing through the center of curvature will have an angle of incidence of 0 degrees, right? Consequently, it will reflect on itself. It will reflect back towards the center of curvature C, center of curvature C. That's one important light ray that you must keep in mind. We have an angle of incidence of 0 degrees. Consequently, it will reflect on itself. It will, in other words, it will propagate back towards the center of curvature C. Angle of incidence is 0 degrees. Angle of reflection is going to be 0 degrees as well, right? So I'm going to put that angle of reflection is 0 degrees as well, right? Consequently, it will reflect on itself. It will propagate back towards the center of curvature C. That's the first thing you have to know to start building your images with this type of mirror. Now, in order to avoid all the trouble of the drawing the spherical curvature inside as it passes. Yeah, provided, yeah, it has, so Raymond is asking, even if the light ray is coming from any side, yes, as it passes, right, through C, it just reflects back. That's right. You know, the condition is that the light ray must pass through the center of curvature. Okay, if the light ray is passing through this position here, then that is not going to happen. Okay, it's not going to reflect back to itself. Okay, it can even be parallel. I'm going to draw here for you. In this case here, yeah, the light ray will reflect back through itself. because it's passing through the center of curvature, right? But what if you have another light ray that doesn't pass through the center of curvature? Even if it is tangent to this other light ray, it's not going to reflect on itself, okay? It's not going to reflect on itself. It's going to reflect at a different angle because it's not passing through the center of curvature. Okay, so let's see. I'm going to format shape, maybe. Yeah, this one here. Good. So that's the incident light ray, right? The reflected light ray is going to be somewhat like, somewhat like, like that. Let's see. We gotta come up with a, the normal will be, okay, the normal will be like that, right? That's going to be the normal. So consequently, the reflected light ray is going to be somewhat like that. Okay? Don't forget, the normal is going to pass through the center of curvature, right? So here is the angle of incidence. And here is going to be the angle of reflection. Okay? Does it answer the question, Raymond? Okay. So it doesn't matter. It can be parallel, even if it's parallel, it's not going to reflect on itself. Okay, light ray, here you go. We're going to write it down. Light ray parallel. Light ray not passing through the center, through C, right? Yeah, let's continue. Center of curvature. It doesn't reflect on itself. And I'm going to draw as well the normal. So you can visualize the normal better. Does the normal not have to be to do with the tangent? Yes, that's right. The normal has to do with the tangent. But there is an easier way of finding this normal, right? The easier way to find this normal is to get the direction passing through the center of curvature, right? I'm going to put that in dashed lines. I'm going to change, that's the normal. Automatically, this normal is going to be 90, is going to be perpendicular to the tangent. Oh yeah, it will be perpendicular. Automatically, this normal here will be perpendicular. If you put, because any line, it's a circular, right? It's a sphere. Well, more specifically, it's a sphere, but no, you can call it a sphere. You can call it a circle. Because it is a circle, anything passing through the radius of curvature is going to be automatically perpendicular to the surface that is tangent to this point. Yeah, okay. And now we have it. It looks like I did a pretty good job, right? Here, angle of incidence, here's the angle of reflection, right? Here's the angle of reflection. That's the type of thing that you have to have a picture, right? You have to have a mental picture, not just a mental picture, but a picture in the paper or in the slide to understand how light ray propagation works. Now, instead of keep on drawing these spherical surfaces, people do, we've simplified those drawings so we can save time, okay? Instead of representing like a circular surface right here that represents the spherical surface, we just, draw a straight line and put those angles here at the edges of this straight line. This representation is a representation of a spherical mirror. It is wait a minute, it's a representation of a concave mirror. A simpler representation of a concave mirror. A simpler representation of a concave mirror. Simpler is this one here. So we're going to be using this representation for a concave mirror for the rest of the course, okay? And now we can go ahead and state the axis of the mirror. This axis passes through the center of the mirror, and it is perpendicular. Perpendicular, it is normal to that point here. Not perpendicular, but normal, right? Because this is a curved surface. We draw the center of curvature, right? Let's do that again. Every time that you are solving problems with a spherical mirrors, concave mirrors, you do that. You draw the concave mirror. You draw the axis of the mirror. This axis again passes through the center of the mirror and is going to be normal to that point where it crosses the surface of the mirror. Pass through the center of the mirror and pass through the center of curvature too. All right. So here you go. I'm gonna have my center of curvature here. Ideally, I should be doing like that. Here you go. I should be putting this one right in here. The axis of the mirror comes afterwards, right? And I'll copy this one and place here. Ideally, I should be showing this, mirror, center of curvature of the mirror, axis of the mirror, principal axis of the mirror. And now we can start playing with light rays. Okay. The first light ray, well, the first light ray you already know, right? I'm going to draw that first light ray. I'm going to take out this one. The first light ray is this one. Light rays that you already saw. Light rays that pass through the center of curvature is going to be reflected on itself. Well, okay, good, I got it. It's going to be reflected on itself. So this light ray, I want to get this simpler illustration there instead. Oops. Put it here. Yeah, here you go. That's the diameter of the mirror, right? The next light ray that we are going to be working with is light rays that are parallel to the axis of the mirror. Okay, parallel to the axis of the mirror, and axis of the mirror, let's put there as well. Those light rays, they reflected at this angle, right? And it crosses the principal axis at a point that is half the distance of the center of curvature. This is an approximation again. Don't forget, this is an approximation. Okay. Let's see if we have that. Okay. DC, I didn't put that here. CC prime, yeah. CC prime over 2, yeah. The light will intersect the axis at CC prime over 2. Okay, so light rays to worry about, right? So light rays to know about. One, I already told you, light rays, I wrote that down exactly here, right? But I'm going to repeat here. Light rays that passes through the center of curvature of the mirror reflect on themselves. Okay? Light rays parallel to the principal axis of the mirror. Light rays that pass through the center of curvature are reflected back on themselves, are reflected back towards the center of curvature. Curvature C, center of curvature C of the mirror, like back towards the center of curvature. light rays parallel to the principal axis of the mirror. Reflect towards the principal, reflect towards a point in the principal axis that is equal to half the center of curvature of the mirror. Right? So if the mirror has a radius of curvature r, if the distance from here to here is CC prime is equal to r, then this point here that I'm going to call F, okay, here you go, F is going to be half of the radius of curvature of the mirror, because most light rays are going to reflect, because light rays that are parallel to the axis are going to reflect through this point. We call this point here the focal point. Okay? Focal point of the mirror. Light rays parallel to the principal axis reflect back towards a point in the principal axis that's equal to half the center of curvature of the mirror. This point F is called the focal point, and the distance lowercase f is going to be half of the center of curvature, and the distance f is called the focal length of the mirror. And don't forget, this is an approximation, right? The focal length of the mirror is half of the center of curvature. This is an approximation. Okay. And that's assuming that the diameter of the mirror is much less than the radius of curvature, because don't forget, this is a, and I'm gonna even put an approximation here. It's an approximation, but it's a very good approximation, okay? Don't make any mistakes here. What else do we have to know? Okay, there's another third ray. Light rays that passes through the focal point are reflected back parallel to the axis, principal axis of the mirror. So now we have three light rays. We have three light rays that we can use to predict the position of our images. Light rays that pass through the focal point F reflect back parallel to the principal axis of the mirror. Can you remember that? And then we have this other mirror, this other light ray too that might be useful, okay? If this one is easy, right? It's easy to, if you have a light ray incident at the center of the mirror, it's easy to draw the fact that it's going to reflect back at the same angle, right? If the light ray were to reflect here, that would be a little bit more difficult, because at this point, you have a different tangent. Here, the tangent is just in this direction, right? At this point, the tangent is just in this direction. So we have a force light ray. A force light ray. A force set, a force set of light rays. Remember, you can have more than one light ray, right? We can have this light ray that you see here. You can have this other light ray that you see here. You can have this other light ray that you see here, right? So it's a fourth set of light rays that we use are the ones that are incident at the center of the mirror. So 4 sets of light rays. You need only 2, okay? But it's always good to know more in case that you cannot draw one or two of those light rays. And sometimes that happens. Light rays that pass through the focal point reflect parallel to the principal axis of the mirror. Light rays that pass to the center of curvature, right? So 4 different sets of light rays. You don't need more than that. Here you go. Now we can start building up images, right, of the light ray. Again, I'm going to switch the position of this guy, and since I introduced the center of curvature first, right, let's axis, focal point, right? And now we're going to start forming images, image formation from our object. Okay, our first light ray. Okay, I made this one as my first light ray, parallel to the axis. And if you memorized everything, this, center of curvature C divided by 2, this light ray reflects towards the focal point. So it's called my object, okay? This arrow here is called my object. And that's what we use to represent objects in geometric optics. Then we're going to need a second light ray. I have chosen this light ray. And it's going to be reflected back, and it's going to intersect. Do you remember the technique that I showed to you for planar mirrors? It's very similar to this technique here that you see. And now we have the intersection here. Intersection of those 2 light rays. Okay? But if you want a third light ray, you don't need a third light ray, but if you want a third light ray, yeah, you can get this light ray that passes through the center of curvature. Okay, and even a 4th light ray, but I didn't put the 4th light ray, otherwise the picture becomes too busy, right? Notice that the 3rd light ray intersects with the other 2 light rays at the same point. Okay, let's see what this book does. What is the notation of this book? I want to keep the notation similar. Images, spherical mirrors. Go. Spherical mirrors. Planar mirrors, that's spherical mirrors. He's doing that. Okay, he's using the letter P. Okay, so I'm gonna stick to the notation of the book. I put it in other books use did not for the distance of the object. Okay, according to your book, this distance here is P, the distance of the object. Okay, this distance here, I'm gonna make it larger. No, not larger, thicker. Ooh. Let's see if I can get, not good, is it? Let's see, thicker, even thicker. Ooh, no, not good. I'm gonna leave the other way. Yeah, that's my image. This distance here, according to your book, we call it I. I for image, for distance of the image. Okay. And let's not forget this other distance here. I'm gonna bring it down. Just to emphasize, remind you, right? Just remind. Now it starts to become busy, right? The drawing. I'm not gonna do that. Not gonna do that. This distance here is gonna be the focal length, lowercase f. Okay. The position of the image can be calculated not just by drawing, but it can also be calculated by mathematical principles. What you see here is just a problem in geometry, okay? That's just a problem in geometry, nothing but that. I'm gonna get my image and put it in the other drawing there as well. And your book goes through the derivation of the equation that I'm gonna show you. You can reduce all those drawings here to right angle triangles, and from those triangles, not right angle triangles, you can reduce to triangles, and from those triangles, then you can calculate, derive an equation for the position of the image. And I'm going to put that there as well. So that drawing is not incomplete, huh? Right here, like that, okay? P and I. And this is going to be lowercase f. Maybe I'm going to move up. Now we have a little bit more of space, right? I think I can illustrate the focal point here, focal distance. Yeah, we have a little bit more of space. And now I'm going to bring it down like that. I'm going to copy that, paste it, and that's going to be focal length f. Hmm. This f is a little bit hidden, right? Let's see, is D1 a distance of the intersection point to the mirror? Distance, makes sense. Is D1 the distance of the intersection point of the mirror? I believe you're referring to the DI, right? The DI is I. I'm changing the notation. What is I? The distance, oh, I, okay, the distance of the image. This is the image. Okay. Distance, okay, here you go. P. I'm gonna write that down there. P. Notation. P. Distance of the object, the mirror, right? I'm gonna put it, this is the object to the mirror. I. Distance of the image to the mirror, right? And you have the F, focal distance of the mirror, focal distance of the mirror, which is approximately, it is an approximation. No, not this one. I want the other one. I want this one here. Distance of the mirror. F is approximately R divided by 2 for a spherical mirror. It's an approximation. Okay. So those are the 3 parameters that you are going to need for the formula that italicize, italicize, italicize. Okay. Notation. Formula. Ooh, not what I want. Yeah, I want this one here. So there's a relationship between all those quantities. It's not easy to memorize. It's possible also to derive. The derivation of the formula below is in section 34.6 is in section 34.6 of the book. I'm not going to derive here because it's going to take too long, okay? But it's very easy to memorize. It's like that, 1 divided by P plus 1 divided by I is equal to 1 divided by F. Okay? That's the relation. Now let's going back to our case here. Notes. Oh, what the heck's going on here? Okay. Notice that I put my object past the center of curvature. Okay. So I'm gonna, according to the drawing, if P greater than R, then the center of curvature, the image of the object is formed between the focal point and the center of curvature. Do you agree with me? Let's take a look. This drawing, that's exactly what this drawing says, right? This image here is being formed between F and C. Can we prove that mathematically? Yeah, we can prove that mathematically. Okay, let's try to do that. I'm doing that on the fly. Okay. Okay, how do we set the bounds of P and I guess would be better. Yeah, the light ray both intersect. Yeah, we're going to do that right now, Raymond. How do we set the bounds for P and I? Okay, yeah, I know what you mean. I'm going to do that right now. Let's do that. Okay. So the example, right? Try that as an example. If P greater than R, right? Which by the way is 2F, right? What would be I, right? Let's see if we can do that. Right? So we go ahead. We're going to write this equation in terms of P. Like that. Right? I'm going to take, I can do it here in this line. I'm going to take the I minus F, right? Common denominator. Right? And then I'm going to invert this equation. When I invert this equation, it becomes Fi divided by I minus F. I minus F, right? But wait a minute, but for this condition here, P is greater than R, right? Which is nothing but 2F. Okay. You know, find what would be F or what would be I. Right now I have to solve this inequation for I. Let's see if you can get that. I'm gonna pass this term to the other side. Right, we have Fi here, greater than that. I am going to distribute this term here. 2FF becomes F squared, right? We don't need parentheses anymore. And we can solve. Let's see, we can solve for I. And the way to solve for I is to pass this term to the other side and pass this other term to the other side. I'm solving for I. Let's see if we get it. Let's see. Yeah, I want to put that between. Oh, I don't need to do that. 2Fi minus Fi is equal to Fi. Fi. Okay. F cancels out with F. Right? And what we get I less than 2F. Okay? Is that what we have there? One more student. Okay, less than 2F, definitely. I is less than 2F. Okay. There must be, let's see, there is one more thing here that I gotta do, okay? Because there is something missing here, okay? In my, let's do, it's not just greater than 2F. P is not just greater than 2F, okay? P is also less than infinity. P greater than 2F, less than infinity. Okay, like that. So you can solve this n equation for those two terms, right? If this term is going to be less than infinity, it means that I must be greater than F, okay? Another condition. Make sense? It has to be less than infinity, greater than this value. So my first condition shouldn't be this one that I found here. My first condition should be this one here, I minus F greater than 0. If it's less than 0, then I minus F, and then this, if it's less than 0, then P is gonna be, less than 2F, is gonna be a negative number, okay? So that's the inequation that you have to worry about, right? And I have to write my P. So before I do that, right? P is equal to that. Two conditions, right? I got one of the conditions, but don't forget, you have to have this other condition as well. What you see here correspond to this condition. What you see here correspond to this condition. So I must be greater than F. I believe that's what you asked, right, Raymond? Yeah, that those are the bounds. Okay. So the best way to write that, those conditions must hold simultaneously. Okay, those two conditions must hold simultaneously. So these two conditions, right, in boldface, let's write it down here. Boldface here. These two conditions in boldface must hold simultaneously. Consequently, we have like that. So go ahead here and here between F and C, right? This is 2F, this is F. So the image will be between this. And there are all sorts of simulations out there about this type of system. Okay, if you go in the internet, 1020, right? Internet. Let's go for the internet. I'm gonna show you what else you can get, and we're going to do more. This is just the first one. Spherical mirror simulation, right? Convex and concave mirror. This one, I believe it's. Let's see. I never click on this one. Let me see if this one is a good one. Yeah, I see. Oh yeah. So let's see. Concave mirror. Let's see. Yeah, they're charging. Yeah, because it's sponsored, right? They're charging. So, but there are simulations that this one must be charged. They must be charging as well. But this one is free. Okay. Okay. So look what we have here. Exactly what I drew for you, right? Object, image. But what we're doing, oops, I can click and drag. Let's see. Yeah, I can click and drag. I am doing this condition here. See the focal point? Call it the focus as well. Here's the center of curvature, CC for center of curvature. Note, see that the center of curvature is 8 units from the mirror. The focus is half of that distance. They put the negative values here for the position. And I'm going to play with this position of the object, right? Look here. The object, the closer it gets to the focal point, the closer to the focal point, the closer the object is to the center of curvature, the closer the image is to the center of curvature too, right? And as I move further and further away, the image gets closer and closer to the focal point. Okay. If I approach if I make a shorter and shorter focal point, you can see that the image gets closer and closer to the focal point. Let's see. Would we say that I is greater than F? Well, no. Let's see. Are you talking about the initial condition or rate? It depends what you mean by F, I greater than F. Okay. So the image renders at the point. Yeah, that was the previous. Okay. Okay, good. So the image range is the point at which the two light rays intersect. That isn't the focal point. Okay, good. Okay, so anywhere you put this object is going to form, anywhere that you put this object after the center of curvature is going to form an image that's going to be between those 2 points, right? And now we can go ahead and play with this equation again, but in a different way, right? In case you still don't believe that, let's come up with a different way of looking at that, okay? What if, here you go, P is infinity, right? Infinite. Find I, right? Solution. Just plug in this relation there, right? If P is a very large number, this ratio that you see here, this one must be, let's put that on the other side, but don't forget it's a plus sign. This ratio that you see here is going to be 0, right? If the P is a large number, this ratio here is going to be 0. Consequently, the image is formed at the focal point. Okay? That's what happens with telescopes. That's what happens to telescopes. Okay? When a telescope is imaging a distant star, it doesn't have to be a distant star, it can be the moon. It can also be the moon. It can also be the moon, the sun, or the planets. Okay? A distant star, right? The image of this object is very close to the focal point of the object. Very close to the focal point of the object. Okay, and by the way, let's see, what is P is not, let's not say infinity, let's say very large. Okay, and by very large I mean, you have to compare very large with one of those parameters of your equation. Okay, by very large I mean much greater than the focal point. Okay, that's even more precise than saying that P is infinity. Now, it doesn't have to be infinity. All you have to do, it has to be much greater than the focal point. Much greater than focal point means approximately, approximately greater than 10 times the focal point, the focal distance. There's the focal point and then there is the focal distance, right? So that's one way. Then consider that another example, right? Example. Now, what about the other one? And by the way, those things, those spherical mirrors are sold in drugstores, okay? Many girls, they buy those mirrors to look at their faces, okay? Because those mirrors enlarge your face to see details. Now, what's P is equal to 2F? Find I, right? Find I. So if P is equal to 2F, now you are going to have this relation here. Okay, and then you are going to pass this term to the other side, and it's going to become easier to solve this equation. I'm going to go on the next step. When you subtract 1 over F, when you subtract 1 over 2F from F, what do we get? You get 1 over 2F, right? When you subtract 1 from half, you get half. Right? And now look what we get. We get that twice F. Those are the limiting conditions of the position of my object. Okay? So we can And then you can do for the other cases. What time is that? 10:29, right? Let's go a little bit longer. I want to finish that before I go into a break. Now we're going to get, let's see, that's the object. We did that. See, yeah, we did that, and then we have our image here. It's just a repeat what we did before. Now let's see. What about if E equal to I? Okay, that's the center of curvature. Yeah, that's an illustration of what happens to the image when the object is at the center of curvature. P equal to the image. I just derived that. Right? Let's go back to my 2F, by the way, which is equal to P. Huh? Image is equal to 2F, which, by the way, is equal to P. And now we got, let's see here. Oh, that's sad. I didn't do it for the other ones. Let's see here. I'm doing for the convex. Yeah. I'm supposed to have the other cases, but let's have our break now. Okay, and I'll get the other cases for you after the break. Any questions? Because before we move forward. Okay, all the other cases are right in here. Okay, so I'm going to do each cases. I'm going to be doing this type of condition. Okay, between the center of curvature and the focus, and then I'm going to do this condition here between the focus and the mirror and the surface of the mirror. So we have three conditions: 1, 2, and 3. Each one of them has a slightly different characteristic, a slightly different result. Okay. Okay, so let's have our break. And break 10:31 a.m. to 10:46 a.m. Okay, so play a little bit with those equations so you become very familiar with that, and I will see you shortly. Okay, so now let's go for our next condition, right? And I'll have to do that from scratch because it doesn't seem that I have the, let's see here. You know what? I'm gonna take advantage of the drawings that I already have. Yeah, okay, yeah, let's do that. Start with the mirror, right? I'm not sharing yet. Okay, here you go. Now I'm sharing. Start with the mirror. Yeah, the axis, the center of curvature, the focal point. That what you have to do all the time, okay? I prefer to start with the center of curvature. And now my object is going to be at a different position. It's going to be somewhere between the center of curvature and the focal point. The upright arrow. And then what you're going to do? No, not this one here. Go. That's going to be the position of my object. Right? So here you go. Now P is this one here. Yeah. Okay, and between the center of curvature and the focal point. And I'm gonna get this line here as well. So you have everything that you need. We don't need this guy anymore. Next is going to be, let's see, I'm using my Okay, the center of curvature. The center of curvature is behind the object. Okay, when the center of curvature is behind the object, what do you have to do? You have to draw your line behind, passing through the tip of the arrow, okay? Like that. Because my mirror is not large enough, my light ray is going to be outside the surface, but that's okay. That's okay because it is as though the mirror was extending all the way up, right? And then the light is being reflected back to the center of curvature. That would be our first light ray. That would be our first light ray. And then we have our second light ray. My second light ray is the one that passes through the focal point, parallel to the axis. Let's see. This one here, this one, okay. Yeah, now I got it. Good. Now we did this light ray parallel to the principal axis. Okay, and exactly what I'm doing. Light ray parallel to the principal axis passes through the center, through the focal points. Okay, and by the way, I'm going to extend this light ray even further away. And now we have more or less the position of my image. Okay, but there's more, right? Let's do one more, just for the sake of it. I don't need that anymore. The other one would be the light ray that passes through the focal point and is reflected back parallel to the principal axis. So here you go. Focal point, focal point. If I did everything right, I have to move my P from there, otherwise it's going to be overlapping with this third light ray, right? Let's move it a little bit down here. We're confused on how to set up the rays for this problem. Okay, so let's do that again. Okay, maybe I'll do in a better way. I'm not going to do it through the center of curvature, otherwise it becomes too complicated, right? So here you go. Mirror, right? Mirror. Next drawing that you gotta draw is the center of curvature, right? We draw the principal axis later on. We're doing that all over again, okay, Raymond? Here you go. Principal axis. Alexis. Principal axis, center of curvature, focal point, and object. So instead of getting it through the center of curvature, let's instead get a light ray, you know, parallel to the principal axis. Okay? So it becomes simpler. I'm gonna get this one here, 1 and 2. No big, all right? So here go 1, 2. See, 1. Yeah, I gotta get this guy here. Yeah, didn't, did. Okay, object here. That's the position of the object, right? And now I'm going to get another slide, repeat this slide, and just get this here, those light rays. This one that I want, yeah. Okay, here you go. Light rays coming from the tip of the object. Light rays that are parallel to the principal axis. The object is the bolded arrow. Yeah, that's right. That's the bolded arrow. See the distance of the object here, P? Okay. light rays that are parallel to the principal axis reflected through the focal point. Okay. Again, you need only 2 light rays to solve this problem, right? And then, you know, previously I had done through the point of to the center of curvature, but you don't have to. You can do this other one here. Light rays that pass through the focal point, yeah, is going to reflect parallel to the principal axis, like that. So, just like I said, you could have come up with the, you know, with the light ray that passed through the center of curvature, right? The light ray that passed through the center of curvature, you know, the backward propagation that would be through the center of curvature. And you can get that other light ray, right? The other light ray that goes exactly at the center of the mirror. Okay, that's the third light ray. That would be the third light ray. And then the fourth light ray would be the light ray of the center of curvature. But let's stop here, right? Now we can go ahead and form our image. My image is right in here and I have to invert it. Okay, and I'm gonna put it in the dashed like that. No, I don't like that. Can do better than that. Dashes, maybe this one. Let's see, no, this one better. That's my image. Note, see that my image here is larger than the object. Okay, note, see that. This image, we can visualize it by putting a screen in there. And by the way, that's how movies are projected into a screen. Oh, movies are projected into a screen using a lens, right? But if you were to project a movie using a mirror, that would be the proper way of doing that. You'd put the object or the film, right, nearby the focal point, and then the image would be focused far away in the screen with a larger size. Okay. If I want to exaggerate, just like I said, you know, I can get that other light ray that passes through the center of curvature. And the light ray that passes through the center of curvature looks just like that. Okay. It's lined up with the center of curvature. The mirror, the surface of the mirror should be all the way up here. Okay. And this one would be reflecting on itself. Okay. Yeah, that's a, you know, that would be around here. Let's see. Yeah, the focal point, if I were to follow the center of curvature, the focal point would be, you know, not the focal point, the other light rays would be like that. And then you can have the fourth light ray, right? Reflecting right at the middle of the mirror. I'm going to do the following. I'm going to increase the thickness of this mirror. Yeah, I'm gonna make it black. Good. So you can clearly distinguish that. And then I'm going to dash it. Okay, like that. I'm gonna increase the thickness of this one as well. So everything is consistent. Lowercase i, and now that is going to be low. No, it's not lowercase I. Is let's see how we do it. Lowercase I is going to be the distance. This one here. Extend this double arrow and put the lowercase I here. Ooh, not this one. Yeah, this one here. Yeah, now we have it. Yeah, object and image. Okay. And now let's go back to the notes, right? Like I mentioned, I'm doing the case of object between center of curvature and focal point. Now, what if less than 2f greater than f, right? Where is the image formed, right? So we go ahead and do exactly the same mathematical procedure. We know that's the relationship between the object, the focal point, and the image, right? I'm just copying and pasting it. Huh? Solution. In this case, the object is going to be at position less than 2f and greater than f. And then all I have to do is to substitute the limits here. Substitute the limits. Okay, we don't have this condition here. We don't have this condition. And now, let's see, I gotta do this from scratch, right? So I repeat, supposed to repeat only part of it. You go, this term goes to the left side and also goes to the right side. Those are two different equations, but those are equations that must be held simultaneously. Okay, I'm going to erase that. In the next step, I'm going to expand this equation. I don't need, oh, I'm doing the wrong one. You go, do this one here. Expand this equation. Oops. And I don't need the parentheses anymore. I'm going to expand the other one as well. I don't need the parentheses anymore. Next. Here's going to be f squared. Oops, I did something here. F squared. F squared. Let's see, we are getting something here. Let's see, yeah, let's stick to this one here. Right, let's stick to this one here. Kartika, here you go. This one cancels this one, becomes Fi, right? And F cancel out with F. Okay, and look what we get. We get that I must be greater than 2F. Okay. And then we have this condition here that doesn't make any sense, right? It's telling us that F squared must be less than 0. Minus F squared must be less than 0. Well, it makes sense, right? Actually makes sense. So it makes sense because F squared minus F squared is less than 0. So you don't have to worry about this other part here because it's giving us a result that makes sense but doesn't have much additional information for us. What this one means is that I is going to be less than infinity. That's what it is. Greater than 2F, less than infinity. That's what this one is supposed to mean. Actually, if you put I very large, right? This term here, it doesn't give us any important information. Okay. The first part of the inequality, the 2, let's see, are you talking about this one here or are you talking about this one here? The first one, this one here, right? Yeah, okay, so here you go. I'm gonna do that for you, and I'm going to pass this Fi here to the left side, right? Make sense? I'm gonna pass this Fi here to the left side. When I pass the Fi to the left side, it becomes minus, and then what's left behind here is 0. But when I pass to the right side too, we get the same thing here, right? Now you do the math here, right? Okay, you do this math there. And so we get Fi, right? We get 0. We get 0 here. This condition here is kind of obvious. There's nothing wrong about that. So, but it doesn't have any additional information. The inequality that has information is this one here. Is this one here. Okay. One more. Here you go. And that's exactly what we see for this one, right? And let's go to our simulation, right? My simulation is this one here. My object is going to be between the focal point and the center of curvature, okay? You can see when the object is exactly at the focal point, something interesting happens, right? Let's do that. I'm gonna show you the simulation, then we're going to derive it mathematically. And in order for you to see that more clearly, I'm gonna put the focal point closer to this surface, okay, of the mirror. Now look what happens, right? As the object gets closer and closer to the focal, as the object gets closer and closer to the center of curvature, it's something that we already saw in the previous situation. The object, the image, is located at the same position, has the same height, but is inverted. As the object gets closer and closer to the focal point, look what happens. The image keeps on growing larger and larger in size, okay? At the point where the object is exactly at the focal point, look what happens. there are two reflected light rays. One reflected light ray is the one that passed through the center of curvature. The other reflected light ray is the one that passed through the focal point. But both reflected light rays are parallel to one another. They will never intersect. Okay? That's what we call an improper image at this point. The image is formed at the infinity. Okay? Just a little bit off this point, you do form an image. It's a very large image, by the way, so large that doesn't fit here inside this screen, right? If I decrease the size of my object, you start to see the size of the image. Okay, you start to see the size of the image. So this, what you see right here is just the implementation of those equations that you saw. Okay, now when it's exactly positioned at the focal point, the image is formed at the infinity. That's the improper image. Okay, so now we can go ahead and do that special case. What if P equal to F? If P is equal to F, comma, oops, what is I? Okay, so we're going to use my equation. Even better, we're going to do it from scratch. We're going to use that from scratch. That's easier to see in the original equation. Okay, P equal to F. F here. What happens? 1 over F cancels out with 1 over F, right? And 1 over I is 0. If 1 over I is 0, that implies that this image is formed at infinity. The image is said to be improper. Where is the infinity? Oh, here, infinity here. This image is formed very far away and is said to be improper. That's the second case. And by the way, now you can start seeing that there are different types of images. Note that there are at least 2 types of images, right? The improper image, and the other one that you saw. Okay, that other type of image is called, which is called real image. A real image is an image that can be projected to a screen. Okay, this image that you saw there in the previous 2 conditions, this image that you see right in here is called a real image. The other image that you saw also for the other condition is also a real image. This image that you see here is also a real image. The only difference is that this real image is formed between the center of curvature and the focal point, right? And the other image is formed after the center of curvature. Okay, so here you go. Let's keep track of what you're doing. We didn't finish all the conditions yet, okay? So I'm going to summarize for now before we go to the 3rd condition. If P is greater than 2F, comma, I is going to be greater than F and less than 2F, right? Image is inverted and its size is less than the object, than the size of the object. Than the size of the object. The object. Now, if P is greater than F and less than 2F, no, less than 2F, then image is formed at 2F. Image is inverted and its size is less than the size is greater, its size is greater than the size of the object. Image can also be projected to a screen and is said to be real. Okay, like that. Now we are going to do the third case. P less than F greater than 0. Okay, let's see where the image is formed now. Let's see where the image is formed now. Okay, and we gotta do the same thing that we did before. And I have it here. I'm gonna separate those slides so we can get it to see here. That's okay. One first case. Second case. And then we have this third case, right? That's the second case. And now we're gonna have this third case. In this third case, the object is between the focal point and the mirror. 3 different conditions. Okay, we don't have this object here anymore. Just like before, right? The light rays that pass through the center of curvature reflect back on itself. So I'm going to put 2 arrows here. Okay. Next, light rays parallel to the principal axis reflect back towards the focal point. Better, okay, right? So now we have 2 light rays, but pay attention what's happening here, very interesting. Light ray, this light ray is passing through the focal, through the center of curvature, consequently is reflected back. Notice what's happening here. The distance here between those 2 light rays is greater than the distance here. It means that this light ray here is diverging from this light ray to the left. Okay, so they're not going to intersect each other on the left side, but they are going to intersect with each other on the right side. See that? So that leads us to a different type of image. So where would the object be for this case? Yeah, we're gonna get there. The object, not the image, right? Where the image would be in this case, right? The object is between the focal point and the mirror, right? See that? See here? It's between the focal point and the mirror. Yeah, before F. And now let's extend those two lines, this one and this one. And bingo, the image is no longer in front of the mirror. It's no longer forming in front of the mirror. This is a special type of image. Okay, the image is forming behind the mirror. Not only the image is forming behind the mirror, but the image is straight. See that? And the image is also larger than the object. There you go. Oh, this is P, right? P is here. This is P. Okay. And I gotta fix that, right? Let me fix that. Not this one, not this one. Yep, not this one. One more, right? You know, I don't need this one. I don't need this one. I don't need this one. Do I need another one? Yeah. Okay. Okay. I'm going to make another slide so it can be P greater than 0, less than F. Okay. This one here. All right. That's the foundation we're dealing with right now. Makes things simpler. Right? First, we document where P is, and then we start using the light rays, this light ray. And then if you want, you can put another light ray there as well. A light ray that passes through the focal point. A light ray that passes through the focal point is going to be similar to the light ray that passes through the center of curvature, right? It's going to be something like that. And we will reflect back, you know, like that, reflect parallel. Okay, and then we have that other light ray that is incident here at the center of mirror and is reflected back. When you extend it back, you extend it backwards, you get that same position. Here, one more. This is going to be I can put my I here. Some book calls it Q instead of I. Okay, other books call it d sub I. This distance here. So that's the last case. Let's do that again. Let's see it again. Here you go. I'm going to get my object, okay, and then the image is forming behind the mirror. This image here is a magnified image. It's larger than that of the object. By the same token that you can use a lens to magnify an object and look at the details of the object, you can also use a mirror to magnify an object, just like we want to, we want to see something close in our skin, right? We get those concave mirrors we buy at drugstores and look at details in the face, in the skin of our face. Now we have this other condition. This one here, okay? If P less than F greater than 0, the image now is going to be less than 0. It's formed behind the mirror. Image is upright. And its size is greater than the size of the object. This image cannot be projected. Cannot be projected to a screen. And it's said to be virtual. Okay. One more student joining us. So you have all those conditions. We covered almost everything. Oh, there is one more thing that I didn't write that down. It's very important. In addition to that equation that you saw, right? The equation that you saw, this one here. There is another two equations that you gotta know. The magnification. The magnification of the object, okay, is gonna be the height of the image divided by the height of the object. And another equation that you can get for the magnification, okay, is this one here. Minus image over object, distance of the image over the distance of the object. Okay. Let's see. Let's do an example. Example. If P equal, we're almost there at our break. F over 2, find I. Okay. Solution. F over 2. Now it's not 2F, it's not F, it is F over 2. Next, F over 2, right? We can pass this term to the other side. Okay. And look what we get. We get a negative value for the image. Okay. We get a negative value for the image. And the image is even minus F. And this negative value means what? This negative value means that the image is virtual. Image that you cannot project into a screen, okay? On a screen. And what about the magnification? Let's use the equation for the magnification. Okay, here you go. The image is negative, the magnification is going to be positive. Okay, here image is equal to minus f. Position of the object is going to be f divided by 2. Okay, the negative sign cancels. The 2 goes upstairs. And the f cancels, right? So the size of the image is twice the size of the object. Okay, the size of the image is twice the size of the object. The positive sign here means that the image is upright, even though we have a negative number here. Okay. And we can do the same equation calculation for the other ones. Okay, let's see. See here. Oh yeah, we didn't do this condition yet, right? The genetic. Let's see. We still have time to do that. If P, yeah, let's see if we can do this condition before our break. P. Let's start with this one. If this one here. P greater than 0, less than F. Oh, like that. Yeah. Right? What we get? This one goes to the right side and goes to the left side, right? Let's do that the left side first. And the right side we don't need because it's going to be multiplying 0. So we end up with 0. Okay. If, find I, position of the image. Next step. That's the only thing we didn't do, right? F goes to the left side first. Oh, and cancels out in the left side. But nothing happens here. Okay. Next step. F cancels out with the F. Right? We are left with this situation here. Now, let's see. Oh, we gotta do more than that. We gotta do more than that. Image. Let's see here. We have I to the P is Fi, focal point, Fi 0. Greater Fi, less than F, greater. Nothing wrong here, right? F minus F has to be greater than 0. In order for this to be greater than 0, okay, this one must be negative and this one must be negative as well. Okay, so P. Oh, let's leave this way for now. We're running out of time here, and I'll get back to you on that. Okay, so those are the conditions. I'm trying to get that for you. But anyway, the I is going to be less than 0. That's what's supposed to be. Okay. Did I do that here? Find I. I will have to be less than 0. I'm not getting that right now, but I can't. Let's see. Yeah, I cannot get it on this one. Yeah, there might be something wrong in that I'm not picking up right now, but let's leave it for the next one because we are in their break right now. Okay, it's gonna be our lunch break. Lunch break 11:35 to AM to 12:05 PM. And after the break, we will have our first lab. Okay. Any questions? Okay, so I see you in 30 minutes. I'm back here. Okay, so just to quickly remind what we're doing, right? Okay, so here's the relationship, right? For the P must be greater than 0, less than F. When we substitute this relation in here, okay? This condition here automatically tells you everything that you need to know, okay? For something like that to be greater than 0 all the time, okay? If I is greater than 0, I would also have to be greater than F, okay? So this for something like that, this ratio here wouldn't be such, this inequality wouldn't be satisfied. For this ratio here to be true all the time, I cannot be greater than 0. It has to be less than 0 all the time. Okay? If I is less than 0, if this term here, the denominator, right? The numerator, right? If the numerator is negative, then the denominator must be negative as well for this condition to hold all the time. So if I is negative, when you subtract negative from a negative, you still get a negative. Negative divided by a negative is going to be greater than 0. So that's the condition for I whenever we have a situation like that, okay? I will have to be less than 0. That's the condition that we have. Final condition here for the mirror. And now we are going to have our first lab. I gotta get organized here. Let's see who is here now, and then can get that's going to be attendance, lab attendance, right? It's going to be one, huh? And today is the 21st, and I'm going to take attendance for the lab. Number. Okay. Here you go. Okay, Eugene Choi. Is he here? I don't see it. Ashley Shu. I don't see Ashley Shu either. Zakir Faris. No. Andy's here, right?
Yes.
Okay. We already have a group. Andy, he. Are you here, Andy? Okay, so you do not have a group yet, right? Okay, you need a group, Andy. So I'll get back to you. Alex Hernandez. Are you there, Alex? You see Alex here. Hello, Alex. Are you in front of your computer? I'm gonna put a star here now under Alex's name. And next is Emily. Emily who? I don't see Emily. Next is Sartak. Okay, you are here. You already have a group, right, Sartak? Basilio Lopez.
I'm here, Professor.
Thank you. Stephanie. Let's see if Stephanie is here. Doesn't look like she's here. Nope. Jeshwan Mohan. Hi, Jeshwan. Jeshwan is not answering me. I'm gonna put a star. Zaid. Let's see. Okay, good. Thank you, Zaid. You already have a group. Alisa.
I'm here.
Thank you. You also have a group. Karthika, right? Karthika. And let's see. Hello, Karthika, are you there? Hello, Karthika, are you there?
I'm here.
Okay, thank you. So you have a group too. Mary,
I'm here, Professor.
thank you. You have a group as well. Raymond is here, right? Good.
Yes, I'm here.
Okay, you have a group. Ashley Tai,
Yeah, I'm here.
you also have a group. Kirakus, I don't see. I need Alexis.
Here.
Okay, you don't have a group yet, right?
Not yet.
Okay, so let's see how we're gonna do that. So there are two students who do not have a group. Let me finish. Let me finish here. I'm gonna put a question mark here. And then there is another student that doesn't have a group. I saw Alexis here in my list, but he's not answering. Okay. Now, Daniela is not here, right? Not here. Sydney?
I'm here, Professor.
Okay. And Sumana? Are you here, Sumana?
Here.
Okay, thank you. So, okay, now, Alexis, are you there, Alex Hernandez?
Yeah, I'm here.
Okay, good. So now, and I need to assign you to a group. Okay, why don't you join? Do you know there is Alex, right? Alex Hernandez, and there is Alexis Madrigal Valley. Okay, why don't you join forces in a group? That's okay? I'll put you in group number 5. And you can exchange contact information. Oh, there's still Andy. Oh, Andy doesn't have a group, right? Andy? Yeah, okay. So I don't join the group. Join the group with the two Alex, okay? One is Alexis and the other is Alex. Join the group with the other two students. You can exchange in contact information through Canvas, through the Canvas email. You're going to be group number 5, and I'm gonna give you a link to your group folder in my Google Drive. Okay, and let's get sorted here. Name, no, it's not name. I'm gonna sort it the group. And we still have some, oh no, I don't wanna do that. I want to do that. Sort group number. Like that. So far, everybody who's present now has a group. 14, okay. 15, one more. Joshua, are you there? Okay, Joshua must be away from his computer. And, oh gosh. Mm, see. Okay. Do it this way. Sort group number. Okay, now I have it. Nope, it's not what I want. This way. Or okay, now it's the way I want. Good. Okay, so okay, group number 5, Andy, Alex Hernandez, Alexis Valley. Do you already have your, make sure whenever you're ready, I will send you a group folder, okay? Whenever group 5 is ready, if they are, once they have already gotten each other contact information, let me know and I will put together a group folder. And we have 2 hours to do that. We'll be able to do it. And wow. Oh, data folder. Okay, so what I'm gonna do, I'm going to upload your data to your group folder, okay? Let's make sure everything is in good shape here and everything is in the way it's supposed to be. Before I distribute everything to you, let me stop sharing momentarily. Remind me when I have to share the screen again. Okay, this one looks good. This one looks good. This one looks good. This one looks good. One looks good. This one looks good. What's that? One. Results. Okay, okay, good. So raw data. I'm gonna copy that elsewhere. Good. And one more thing here before we go. Notes. Okay. Okay. Okay, good. See, okay, so we have it here, and I will walk you through this experiment. Okay. Yeah. 3. Okay. Good. Now I'm going to upload this data of yours to your group folder. Google Drive. This one. Google Drive. Group folder. Okay. Group 1. You have your spreadsheet there. Your data is in there. Group 2. Your data is in there. Group 3. Your data is in there. Group 4. Your data is in there. I'm going to create group 5 now. Group number 5. Good. How is group 5 doing there? Did you already exchange your contact information, group 5? In trouble seeing where to chat, the chat on Canvas. Okay, you cannot, you won't be able to chat on Canvas, okay? I need you, Andy and Alex and Alexis, I need you to exchange emails through Canvas. Let's see. There's no chat on Canvas, but there's an email, okay? As far as I understand, there is no chat on Canvas. Here you go. If you go, see, this is a student view, right? I'm gonna show you student view. Okay. See, Andy, on the student view, you should be able to see inbox here. Okay. Access denied. Ah, interesting. Okay, you folks don't have inbox there in Canvas? That should be, that's strange. You know, I usually get emails from my students, so I'm surprised that I cannot. You got it? Ah, okay, good. Yeah, for some reason, my student view access is denied. That's so strange. Yeah, something wrong here, the student view. But anyway, when it's not in my student view, I can see you folks, right? Make sure you go favorite courses, right? And that should be physics 39. Right in here, if I want to write an email to Alexis or Alex or Andy, let's see, Alex Hernandez, see, there's Alex Hernandez and Alexis. And if I look for Andy, right, you know, Andy, he, good. So that's how you look for him. Okay, good. So you're rolling, right? Good. And did I put the? Still didn't put the. Let's see if I put group 5 there. No, I didn't put group. I'm gonna put it right now. So you have your file spreadsheet. Oh, yeah, it's here. Good. And look at the format that I have, right? P39L01G5. Don't change this format. Keep it this way. I want that organized this way in my hard drive. Okay. Both the spreadsheet and the so-called hard copy. The hard copy Word format, Microsoft Word format will have exactly the same name. Okay. So we're doing that for the first time, and I know that there will be some difficulties at the beginning, but then let's see, I'm gonna share this. Anyone is the link viewer, I'm going to allow you to edit, but okay, group number 5, don't share this link with anyone, okay? Don't share this link with anyone, and I'm going to send you all, just share this link with your group members. Let's see. I'm going to, I need to start sharing the screen, right? Here you go. Done. Right in here. And now chat, Andy, keep, okay, Andy and Alexis, keep this link in a safe place. And don't share that with anyone outside your group. Group number 5, store this link in a safe place. So I'm sending this message to Andy. I'm gonna send that to Alex. Alex, please confirm that you got it, and the other Alexis. You all got hold of each other, by the way? Okay, so what's the script for this activity, right? Step by step. This one here, yeah. Lab 1. Lab 1. Well, the more precise topic for this lab is simple pendulum. Okay, simple pendulum. So we study the theory behind this lab at the beginning of the course. Okay, the simple pendulum motion is approximately that of simple harmonic motion. It's an approximation. Simple pendulum motion is an approximation of the simple harmonic motion. First order approximation, we can say. It's not exactly, because the simple pendulum, is a simple pendulum motion is a simple harmonic motion only for the small angles, right? It is SHM only for small angles of oscillation, of amplitude and oscillation, small angles of amplitude and oscillation. Okay, that's what you have to know. And let's see, let me get some more material here. We can proceed with that. Lab 1, so okay, good. Let's see if I can get reports. So documents must be here. No, it's not here. I gotta look elsewhere. Let me try something else. When is the lab due? The lab, yeah, that's right. Let's do the lab first, and then I'll advertise that. Okay. That's P39 illustrations, activity lab presentations. That's the one. Let's see. Okay. Well, doesn't look like I have what I'm looking for. Yeah. Let's see. Let me try something else. P38. P38 illustrations. Yeah, it looks like I'll have to do that without my PowerPoint. I have so many PowerPoints. I need to organize that nicely here, so I don't struggle finding them. Backup. ACCD. Illustration courses, paste. That must be this one. Illustration. Okay, must be here. Nope, that's not the one. App slides. Yeah, must be this one here. Simple harmonic motion. Let's see if it's this one here. Oh yeah, that's the one I want. Cool. Wow. Sometimes it's so difficult to find that. Okay. So that's how your simple pendulum looks like. Okay, it's a bob attached to a string. The length of the string is much larger than the diameter of the bob. Consequently, the bob can be modeled as a point particle. Okay, so that's okay. So here you go. Lab 1 simple pendulum. The system is a very simple system, right? The simple pendulum is a very simple pendulum. Is a very simple system. Is a very simple system. It consists of a string, a small mass, and a small mass. That's it. Nothing else. A string and a small mass attached to the string. Okay, a string of length L and a small mass attached to a string. The largest dimension of the mass is D, where D is much smaller than L. By much smaller than L, I mean that D is less than L, 10% of L. That's what we mean by much smaller. That's how you quantify this symbol here, okay? So if the string is 1 meter long, if the largest dimension of your mass is 10 centimeter, because it doesn't have to be a bob, a sphere, right? It can be something that's that has an odd shape, okay? So if it's 10 centimeters or less, then it's still considered a point particle, okay? Largest dimension of the mass is D much where this, and under this condition, okay, the mass is considered a particle. Okay. So one end of the string is attached to the mass. The other end of the string is attached to a point of rotation. Okay, that I'm going to quit this one, and I'm going to quit the other as well. Save it. Wait. Here you go. Okay. And here you go. When we put this mass to oscillate at an angle that less than, let's say, 10 degrees, right? That's considered a small amplitude. This motion will end up being very similar to that of simple harmonic motion. In order to solve this problem, we solved this problem before, right? We have to identify the forces attached to the bob. The forces are the weight and the tension in the string. We come up with a differential equation of second order. Okay. And we solve the problem. And we get that under certain approximations, this problem reduces to the differential equation of the simple harmonic oscillator. That's what we do. And then the steps are very easy. You displace this mass from equilibrium, 10 degrees or less, let it oscillate, count how many oscillations. Let's take a look at it. Let's take a look at your spreadsheet, right? Let's see, I don't want that. I want the other one. Close it. Okay, that's the spreadsheet here. In this experiment, what do? We change the length of the oscillator, and then we time how long it takes for the bob to complete 10 oscillations. Let me see. Yeah, 10 oscillations. Yeah, 10 oscillations, okay? Divided by 10. And we repeat that 3 times, okay? We keep on cutting down the length, cutting down or increasing the length of the string. In this case, in this specific spreadsheet, the students recorded the length as being 22.3 centimeters, and then increased to 45 and so on, okay? All the way up to 2 meters, 1.6 meters, all the way up to 1.6 meters. You already
Professor,
have your acceleration.
Sorry to interrupt.
Yeah.
What was that change you just did? I saw the divided by 10. I can't remember where you did it.
Yeah, let me explain. What we are going to do, what we do in this experiment in real life, right? Because this is just a virtual experiment. For instance, the first step, we get the string 22 centimeters length, right? And then we time 10 oscillations. That will be T1. Here the students got 9.5 seconds. And then time a second time. Repeat that a second time and a third time. You can see that it's slightly off, right? But it's 10 oscillations, right? You release the mass and count 10 oscillations. There's a reason why we do 10 oscillations and not just one, okay? The reason we do 10 oscillations is to get a better, more precise result. Then we take the average of the 3 measurements, right? 10 oscillations here, 10 oscillations here, 10 oscillations here, right? Take the average, and after taking the average, then we divide by 10 to get the actual period of oscillation. Here's the period, the average period of oscillation, or here's the average period of 10 oscillations. And here's the average period of one single oscillation. I am dividing by 10 because I counted 10 oscillations for 1, 2, and 3. Okay? Make sense?
Yes, thank you.
Okay. And that's what we do. And then we increase the length, increase the repeat, increase the length, and so on. Okay. That now what you have to pay attention here, very important, the units. Okay, make sure you get the units. I got the units here for you. I got the units here for you. You gotta fill up the units here as well. Okay. Okay, here there's no units because it's a log. Okay, I will always be correcting for the unit. And then, we are going to plot, once you do that, we plot a graph. Plot a graph, and let's see, notes, this one here. Let's take a look at this one, this old simple harmonic Cartesian. See here, lab notes. Yeah, the equation that we are going to use is the equations for the period of oscillation of this of the simple pendulum. Okay. And what are we going to do? We are going to plot T against L. Okay. T average, actually, T average against L. T average versus L, and that's what is written here. And then you're going to get the coefficient. And there's more. It's not just a linear relation, right? You gotta, yeah, it's going to be a power. Okay, here you go. Plot the graphs. First, T average versus L. I'm going to copy into the actual notes, okay? So we can have everything in a single place. I'm going to copy that here. Experiment, simple harmonic motion, copy and paste, and then I'll go through that with you in detail. Yeah, right in here. Notes. Now let's start a new page. Okay, lab 1, simple harmonic motion. No, simple harmonic motion, no, simple pendulum. Font a little bit larger than the other ones. I'm not gonna. Lab 1. Simple harmonic motion, okay? Theory behind the experiment, we covered that before, right? You can either use the Cartesian coordinate system of the polar coordinate system, and then you have to ask yourself which one is more convenient. In the Cartesian coordinate system, the coordinate x and y are both a function of t. However, in the polar coordinate system, here we're just reviewing what we did in the lecture, right? However, in the polar coordinate system, the coordinates with the coordinates r and theta, the coordinate r is going to be a constant equal to the length of the string, right? And only the other coordinate is going to vary in time. Okay, consequently, if you have the following situation, Cartesian, this is going to be a function of t, both is going to be a function of t, but here in this case, we have a simpler situation in which only theta is going to be a function of t. It will be easier to solve your problems, use the second coordinate system, right? And then when you solve everything, you get this relation here. At time t equal to 0, your theta is going to be equal to the theta naught, which is the amplitude, the maximum amplitude. If you work out the period of this pendulum, you find out that the period is going to be equal to this equation that you see here. It's going to be a function of whatever you have here inside the argument of the cosine. Okay, the period is directly proportional to the square root of L, the square root of length, okay? It's very easy to remember that, okay? It is very easy to remember this relation. All you have to do is to visualize right? A large dog is to visualize two different dogs walking, okay? Two different dogs walking. A large dog and a smaller one. And a smaller one. Large dogs have long legs. The smaller dogs, like the Chihuahua, have a very short leg. So if you pay attention to the steps of the Chihuahua, right? The Chihuahua walks very quickly, right? Why is that? There's a reason for that. Okay. Whereas the large dog, you know, he walks more slowly, right? What does it mean more slowly? It means that the period of oscillation of their legs is different. That's what it means. The period of oscillation of the legs of the larger dog takes the natural period of oscillation of the legs of the dog, of the larger dog, takes longer than the natural period of oscillation of the leg of the Chihuahua. Why is that? Because of the size of their legs. Okay, so T is going to be proportional to L, but it's going to be proportional to the square root of L. So if you forget about this exact equation, at least remember that the period, at least remember the period of oscillation of the legs of those two type of dogs, right? And you will remember that the period is going to be proportional to the length of the oscillator. The longer the oscillator, the larger, right? The length of the oscillator, the longer it takes for it to move a full period. Okay, in this experiment, we determine the period of 10 oscillations for 8 different lengths. That's what we did here. 8 different lengths, yeah. Measurement 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Lengths 22 centimeters, 45, 65, and so on, all the way up to 1.6. So we performed this experiment once, twice, and 3 times. All of that, everything that you see here, I tell my students, is raw data. Everything that you see here is raw data. Actual data that you can collect. Everything else are not raw data. Everything else are just results that we process. Okay? Raw data, process data, right? Process raw data, and so on. Okay? There's an important difference between experimental data and results. So that's what we have. Let's see, I'm not sure if you can make a power fit. Oh yeah, that's why you have to use Excel, right? Actually, that's why you have to use Excel. I do not know about Google Sheets, yeah. And Google Sheets is very, especially if you are using the one in the internet, right? They don't have as many features. So if you go to Excel, we upload our final Excel spreadsheet later. Ideally, you should be doing it now, okay? So see if you can get the Excel spreadsheet. I understand that the college offers those Excel software for free. Do you upload? Yeah, that's right. You upload the final Excel spreadsheet to your Google folder. Yeah, that's right. But ideally, like I mentioned, ideally you should be having that. You should be doing that right now. Make sure everything is right. Since you're doing that for the first time with me, my labs are a little bit different. Okay, but yes, you do that. You upload your final spreadsheet to your Google folder. You and your group members, right? So let's go back. Continue here. 10 oscillations. Okay, T average is in the Y and L is in the X. So let's start plotting those graphs, right? If you have Excel, T average and L not this one, this one here, power equation. Okay, let's get our power equation here. Insert chart, scatter plot. Use scatter plot all the time. Click here, right click, add trend line, and here you go. We have power equation right here. Display equation on chart, display R² value on chart. Okay, those are the few labs that I ask you to fit an equation other than the linear one. So I do not know, Raymond. I do not know how to transfer the Google Sheet to Excel. Maybe it's just a matter of copy and paste. You know, I never worked with Google Sheet in the past, but make sure you have Excel installed in your computer because it's a requirement for this course. Okay. Oh yeah. Okay. So, or maybe just download the Google Sheet and open Google Sheet from Excel, right? Actually, maybe that also works. I never did that, but I suspect that you can open the Google Sheet from inside Excel. Maybe that would work as well. Okay, so that's what I have, and let's zoom in a little bit. Let's zoom in a little bit. Look how nice it is, you know? This is actual real life experiment, okay? Experimental data. And look here, the X is the L, okay? Don't forget to label the axis, right? Gotta label the axis as well. You click it here in the chart design, add chart element. We did that before, right? Axis title, primary horizontal, and then you go ahead L and you put in between parentheses the unit. Now will be meter in this case. Now look at the power of L. X correspond to L. Y correspond to T average. Let's put the element here. The vertical. T would be T average. Oh yeah, they did that for me. Isn't that nice? And in your professional life, you'd be doing that a lot, okay? With graphs. I do that all the time. I'm writing a report now for my funding agency, and I'm doing all of that stuff. And the report has to look nice because those guys are giving me money, right? Here you go, T average. Don't forget to put between parentheses as well. Let's see. Gonna be a little bit tricky. Subscript. Yeah, good. Oh no, it didn't, did it? Ay, 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 ay. Okay, parentheses. Oh yeah, here you go. Seconds. Okay. Boldface. And you can do better with those numbers too, okay? Let's see if I'm missing any messages here from you. Nope. Yeah, you can do better with those numbers. Don't leave that, these numbers specifically, don't leave that in scientific format. Leave it in a different format, numeric format. And this one here should be 16, maybe 16 is too large, right? Let's try 14 size. Yeah, font, here you go. This one is 10. Now I don't want 10, I want at least 12 to make the second look nice. You know, italicize it. Give a little bit of space between the average and the parentheses. I'm going to italicize M. I'm going to italicize L. And I'm gonna change the font size here. The font type, right? The font type. And let's see, how do I do that? Yeah, font, no, that's not the font type. It's the font format. You go number right in here. You don't want scientific. Okay, you want actual number. And then you put 1 decimal place, maybe 2 decimal places, if it fits. Yeah, 2 decimal places is good enough. Actually, 1 decimal place is better. Right, 0.2468, 1.0, 1.2, 1.4, and so on. Okay. You can do more. You can do more. Notice that we have this big blank space here. And also we have this big blank space as well. By the way, this axis here, I like to put it in boldface. Spend some time doing that in Excel. The seconds, they don't have to be in scientific format either, right? Let's get it here. Okay, click right in here for graph and then go to number. Don't leave it in scientific, leave it as a number. We need 1 decimal place or 2 decimal place. Let's see 1 decimal place, how it looks like. Yeah, 1 decimal place looks like enough for me. Okay. And then I'm going to start optimizing the space. Am I going too fast? Let me just go through every one, and I wanna know how good you are with Excel, okay? So I have myself an idea. How good are you with Excel, right? And how good are you Excel? Are you experienced with Excel?
I've used it before, but I don't have too much experience with like graphing, but I can learn.
Okay. Okay, so you have some experience with Excel, right? That's all I wanna know. Okay, and I will help you with the rest, right?
Mhm.
Am I correct? You have some experience with Excel. You had some experience with Excel in the past, right?
Yeah.
Okay, good. So Alisa, have you ever had an experience with Excel?
Yeah.
Okay, good. So let me see. I'm gonna put 2 here. And every now and then I'm gonna ask you questions to make sure you're here interacting with us, okay? In the lab. Ashley, are you experienced with Excel? Not highly experienced, but just some experience, right?
Yeah, I know how to make graphs.
Okay, good. So next is Sartak. Sartak or Sartak? Let me say. Are you there? Let's see. Yeah, Sartak is here, but he's not answering. Huh? Oh yeah, I have some experience. Good, good. Thank you. Thank you. Mary, do you have any experience with Excel?
Yeah, but very little.
Okay.
No, yeah.
You'll be learning. You'll be learning a lot about Excel here. So I
Okay.
try to. It's very, it's very important. Like I said, I'm a professional and I don't use any fancy software. The software that I use is Excel for writing my papers, plot my graphs. When I collect data, I plot it, with my experiments. And okay, no experience. Okay, I'll help you out, Raymond. I'll help you out. Basilio must already have experience, right, Basilio?
Correct.
Yeah, Basilio took the class with me, so you're in the past, so he already knows some of it. Let's see, Jeshwan, are you there, Jeshwan?
Hi, I'm here.
Okay, good.
Sorry for
So
missing that.
do you have any experience with Excel?
Yeah, I have a little bit of experience.
Okay, good. So Zaid? Okay, got some experience. Good, that's great. And Karthika, right? Karthika.
Yes, I've experienced with Excel.
So, you have some, right? You broke up when you said something. So
Yes, I do have experience with Excel.
okay, good. Thank you. Andy? Andy is not here, huh? Wow. Okay, I'm gonna put a star here for Andy. Alex Hernandez. Do you have any experience? Yes, okay, good. And next is Alexis.
Yeah, I have some experience.
Okay, good. So you go more here. And Sydney. Do you have any experience with Excel? I can't hear you, Sydney. Okay, I'm gonna put a star here. Then Sumana, do you have any experience with Excel?
Yeah, a little bit.
Yes, okay. Okay. So you said yes, right? And let me 15. We have okay, someone left, right? Was that left? Have 15 here and 14 there. Who was that? Andy. Okay, Andy is no longer here. Okay, so I'm going to put 0 here. Okay. Raymond, I don't know how to get that explanation. Yeah, we're gonna do that. Don't worry. Don't worry, we're gonna get there, Raymond. Okay, and okay, so I got an idea and how experienced you are with Excel. And let's plot this graph again. Maybe I went too fast, right? Let's do that again. Let's plot this graph again. You know, there is something about Excel that took me a long time to learn. I learned only after, you know, struggling a lot with Excel. One of the things that I struggled with Excel is if we get 2 columns, if we plot those 2 columns here, which one is going to go in the X and Y axis? That was my question, right? Unfortunately, Excel, every time that you have a table like that, unfortunately, okay? Every time you have a table like that, whichever is to the left is going to end up in the X-axis. So it's going to be L that's going to end up in the X-axis, okay? Article. If I highlight T and L, it's going to be L that will end up in the X-axis. So let's go insert it. Everybody know how to highlight here those 2 columns? No problem here. There's a little trick to highlight those 2 columns separately, right? Do one, yeah, that's right. And then there's a little trick there, okay, Raymond? Okay, so you highlight the L first, okay? To highlight the T, if you don't do anything, you know, the other highlight disappeared, okay? Just like you said, you can only highlight one at a time, right? But there is a little trick to that. You highlight the first column, okay? I'm presuming that you are using a PC, right? Not a Mac. Is that right, Raymond? Are you using a PC instead of? Okay, good. So since you're using a PC, what do you do next? You press the Control key, just like I'm pressing. Oh, you're using, oh, you're using a Mac today. Okay. Okay, if you're using a Mac, let me see. The Mac is a little bit different, okay? So here you go, you highlight the L. I believe you press the Apple key, and then you go ahead and highlight the T average. Try that. You know, I used to like Macs, but then, yeah, this is the Apple key, right? Yeah, so, okay. For everybody else who's using a PC, right? If you do not know how to highlight those 2 columns, first you highlight the L column, you press a Control key and highlight T average. Okay? For the PC. For the Mac, you press the Apple key. We're good? So insert, always use scatter plot. Always use. There will be, you know, some exceptions in which we are going to be using other types of graphs, okay? But this is the one you're going to use most of the time. This is the one you're going to use most of the time. So first thing, you know, we are going to, first let's get the regression equation, right? That's all spelled out how to get the regression equation in my syllabus. You click one of the data points. When you click one of the data points, you click everybody gets highlighted. And also, not only everybody in the graph gets highlighted, but the columns too. See that? The columns get highlighted. It's nice. It's a nice feature in Excel. So you know, you know which data this graph corresponds to. It's a really nice feature of Excel. Next step, right click. Right click. Okay, and then you go to add trend line. That's where you're gonna get your regression equation. The regression equation is the equation that most closely approach the data that you have. Most of the time we get straight lines, okay? Most of the time, but this is an exception. Add trend line. See, by default, Excel chooses linear by default, but you don't want default, you want power. You want power, and then go down here in this pane, display equation chart, display R square value on chart. I talked to you about R square, right? I discussed what R square is all about. I don't have that option to display trend line when I right click. Okay, let's see. Maybe you should, do you have this option here, Ray? The Mac, I believe, has this option here at the top right. Check if you have this option here, but you have to click the table, the graph, okay? When you click the graph, this plus sign here appears. And then you can see trend line, and then you can choose. Do you have that? Nope. Ooh. Okay. Okay, that's the Mac, right? I need you to figure out how to find that, okay? Uh-huh. Okay. Uh-huh. Okay. Yeah. Okay, see, Macs are good computers. I like Mac. I used to like Mac. Now I use only PCs. My first computer was a Mac. But then PCs, got caught up with Mac. In the past, Mac had a much had the best interface, user interface, okay? And the PCs still didn't have this window interface. And then when Microsoft Word started to improving their interface, the Apple said that they were infringing on their patents. Eventually, they got an agreement, and now the PCs have a window interface that's very similar to the interface that the Macs always had. Okay, let's go. Okay, so here you go. Everybody is following, right? So we got here the equation. Now look how good this curve fitting is. Okay, X correspond to L, and this X here is raised to the power 0.4948. The theory states that L is raised to the power of half, right? That's what the theory states. When he writes this equation, right? What you end up getting here is going to be like that, right? 1 divided by square root of G, and the L is raised to the power of 0.5. But that data, when it's fit the curve with Excel, doesn't say this is half, but says it's pretty close to half, 0.4948. Pretty good, right? It's going to be 0.05 out of 0.5. 0.05 out of 0.5 is 1% difference. It's 1% difference. Okay? So this power is very close to what you're supposed to get. But there is more, right? There is more. It's not, we're not done yet. We're not out of the woods yet. I usually don't like the title in the graph, so I usually erase it. What do we have to do next? Okay, we have to improve the displays here of the axis, right? On the axis. Double click on the x-axis. And like I did before, let us change the numbers from scientific to number. 0 decimal places is not enough because we have repeated numbers here, right? 0, 0, 0, 1, 1, 1, 1, 1, 2, 2, right? So in order to distinguish from those numbers, we have to at least put 1 decimal place, okay? At least. Now we have 0.0.246812468. Now we can see it. And we do the same here with the vertical. No, numbers, and at least one decimal place, right? Yeah, we got it. And you have to add the chart element too, right? Axis title, primary, horizontal, primary, vertical. We start with primary horizontal is the L between parentheses, meter, right? And then you do for the t-average here as well. I'll be looking for all of that when I correct your lab report, okay? So what else do we have to do? There's a big blank space here, right? So you can adjust that as well. So the best you can do in the vertical, would be 0.5. Start at 0.5 instead of starting at 0. It's okay to start with a number different of 0. It's okay. Maybe you can do even better than that. Maybe you can do 0.75. Let's try 0.75. If we do 0.75, make sure you add another decimal place here to your number so we can see that's 0.75. Yeah. But I think that those numbers are too close, right? So you go ahead, adjust the minor, the major. Okay, the major would be every half. Let's see, 0.25 is, let's see if 0.25 looks good. Yeah, 0.25 looks good, right? A little bit too close, but I think it's okay. Yeah. What else can we do? We can improve this one, right? Instead of starting at 0, we start at 0.2. 0.2, you go, 0.2. Okay, we are eliminating the large blank spaces. I'll leave this way. Yeah, let's see. We could eliminate a little bit of this, but it would be too much. Okay. Don't forget to put the axis title. And then, what do we do next? Our priority is to plot the graph. That's why every lab that we do, the priority will be to plot the graph. Okay, so let's put here this. There are so many things we have to do, right? Sometimes we get lost. Okay. Every priority in the lab is first to plot the graph or graphs, depends, right? And that's what I'm doing here. There are 3 graphs in this lab. There are 3 graphs in this lab. I got my first graph. Let's get my second graph. So first I want to see if everybody has plotted the graph, okay, before we move on. The first graph. Graph 1, right? Amy, did you plot your first graph?
Yeah, my group has.
Okay. Any questions about that?
This might come later, but will you be going over how to calculate the percentage differences?
Oh, the spreadsheet does everything for you. It's already programmed, pre-programmed to do that.
Oh,
Okay.
okay.
The spreadsheet is already pre-programmed to do that, so you don't have to bother with your calculator. We're gonna get there. It's like I said, let's concentrate on the priorities, right? In my labs, the first priority is to plot the graph. Then we worry about the rest. It's the most important one. So Alisa is the next. Do you have the graph plotted there, Alisa?
Yeah.
Okay, good. Any questions?
No, not right now.
Okay. What about Ashley?
Yeah, I have
You have what?
we have all the graphs.
All 3 graphs already? Oh man, I'm behind you, folks. Okay, good. Now Sartak. Okay, this is an opportunity for you to tell me that you're in front of your computer, okay? Are you there, Sartak? Okay, good, you got it. You got our first graph. Okay, good. So, okay, so let's move forward and then I'll call everybody else, okay? Let's do the second graph, right? The second graph is what, T, denotes T square and L. This one you can fit a linear equation. Okay, this one you can fit a linear equation. Why is that? This one, because when you square both sides of this equation, everything else becomes linear, right? 4 pi square. Uh-oh, what did I do here? 4 pi square L divided by G, right? We don't need that anymore. 4 pi square. And look what we get, right? I'm going to do even better than that. I'm going, instead of dividing L by G, I'm going to divide the 4 pi square by G. And now, if we make T square equal to Y, right? L equal to X, and this coefficient equal to A, we're supposed to get a linear equation. The only difference will be the units. And I'm gonna plot that, not this one here, T square and L. Then later on, you're going to do all the tables, okay? Let's first get rid of the graphs. Those are the most important ones. I'm not gonna do the axis, but you're supposed to do, okay? Labels, axis labels, and so on. But we need to put the regression equation here. Display the equation on chart, display R square on chart. Take a look at the R square here. R square is very close to 1, right? Here too, the R square is very close to 1. So it means that you have a very good fit. This equation fits very well. Better than that is just R square equal to 1, which is almost impossible to do that. If you're getting R square equal to 1, you know, you either did something wrong, okay? Or you do not have enough decimal places there, or the data that you got is fake data, okay? The student just fake the data to make it look good. Every time that I see R square equal to 1 there in a real experiment, I question my students. How did you get R square equal to 1? In real life, in principle, you don't get it. There is another possibility too. If you get R square equal to 1, and I have seen that in experiments, and the students didn't cheat, okay? They didn't make any mistakes either. There is this instance in which you have an instrument that does not have enough resolution. It's like measuring, you know, something. It's like measuring the length of an object with a ruler that doesn't have millimeter divisions, okay? Under those circumstances, it may happen that you are going to get R square equal to 1 under those circumstances. And I did get something like that from my students in another experiment, not this one. But, you know, those are exceptions. If you're performing an experiment, you always have the equipment, the instrumentation to make good measurements. So that ruler that they were using were not the right ruler for that experiment. And there was nothing we could do about that. Okay, so here you go. We got this one. And look, we're going to look at this slope later on, okay? But I want you to remind you that this slope is supposed to be 4 pi square over G, okay? 4 pi square over G. Don't forget, G is 10, right? Approximately 10. What about 4 pi square? What do you think 4 pi square is? I want to hear from you. Approximately, you don't have to tell me the exact value. Think about that. Pi is 3, right? 3 squared is 9, but pi is a little bit more than 3. So when we square something that's a little bit more than 3, what are we going to get? Think about that. Okay, and you can use your calculator too. You don't even have to use the calculator to find out, but just with ballpark, you know. When you multiply 4 by pi squared, you're actually multiplying 4 by a number that's very close to 10. Okay, so this pi squared is a number that's very close to 10. So this slope here that you see right in here, 10 divided by 10 times 4, is going to be a slope equal to 4. And that is exactly what we are getting here in my experiment, in my slope. Okay? That's exactly what you're getting here. And finally, the last graph, log of t and log of t average. Right? Insert. Here you go. And we still get a straight line. And that should show in my other, let's see if I have it here. I should have it somewhere. Oh, yeah, here you go. Square root. Let's see. Yeah, that's the one. First graph, second graph, and third graph. When you use the log on the base of 10. Okay, this one is going to be my x. Oh, well, actually, not this one. This one is going to be my x. The L is still raised to the power of half. Half is going to go in front of. So we should get a slope that's close to half. Okay. Did you get that? Let's see. Trend line. Display. Yeah, we did get a slope that's very close to half, 0.4948. Okay, and this intercept should be close to that other term that we saw. Okay, so that's what we have. I want to get a little break. It's 1:21 already. Okay, let's take a little break, and then we. Any questions so far? I want to see here my students. We have 14. Yeah. Sydney, are you still there?
Yes, I am.
Okay, so did you get Excel there?
What was that?
Did you get your Excel spreadsheet?
Yeah, I did, but I don't see, like, I'm not sure if I'm on the right one because I don't see any of my members on it as well. Like, I'm the only one in it.
Oh, one group wait a minute. Are you talking about, let's see, your group 4, right?
Yes.
Okay, did you get, let me see your group 4. Maybe I made a mistake there. Yeah, you have it here, L01G4. So you do have the right spreadsheet. Did you download to your hard drive? You gotta download it to your hard drive, okay?
Yes, I did.
Okay, you did. Okay, that's good. And did you plot the graphs?
I'm doing it right now.
You're doing that right now. Working. Okay, working on that. Good. So 122 right now. Let's get if it's asking for a slope and not coefficient, does that mean it wants a linear equation? We're gonna get there. Hang in there, Raymond. Hang in there. Okay, let's plot the graph first, and then we are gonna get there. We're gonna get there on after the break. Okay. Is let's see, 123. Let's see. But let me see. Let me help you. Let's see if I can answer you right now. Is the second graph right, Raymond? The second graph. The second graph, you have to use this table here. Okay. Okay, that's the second graph. For the first graph, the tables that you have to use is this one here. For the first graph, we have a coefficient. But the second graph, we don't have a coefficient, we have only a slope. See that? Make sense? We have separate tables for different graphs. Yeah, that's right. You have, oh yeah, it's a slope. So, well, you gotta see what happened there, right? I got the right slope. Maybe you made some mistake there, or your data is not correct. The slope should be close to 4. Okay. But we'll talk about that after the break, right? So 124 right now. Let's see. Break 1:25 p.m. to 1:40. Then we have only 20 minutes to go. Maybe you won't be able to finish everything today. Let's see how it goes. Okay, so I see you in 15 minutes. Yeah, that's right. You all should be working together. Okay, everybody in group, Sydney is in group what? 5, right, Sydney? So you should be in touch with each other, okay? Group 4, you're in group 4. So get hold of your group members, right? Kartika, Sydney, and Sumana. So make sure you're interacting with each other, but each one of you must be plotting the graph, okay? And then you turn in a lab report, a single lab report. Okay. So let's see. Stop sharing. Okay. So 20 more minutes to go. Doesn't look like we'll be able to finish today, okay? But let's do as much as we can, and then tomorrow and the day after tomorrow, I tell you what we're going to do, okay? So for now, you don't have to worry about turning the lab report. And the day, let me see, tomorrow is Thursday, the day after tomorrow is Friday, right? So it makes no sense. As the day is Wednesday, tomorrow is Thursday. Okay, so let's take a look at our schedule here, syllabus. Yeah, okay. Okay, Monday I tell you what to do, okay? What we're going to do is this. Let's see if we can. There are some details here that I still didn't tell you. Okay, but let's see. So first thing, priority, right? 1, plot the graphs. Okay, that's the first thing that you have to do. After plotting the graph, fill up the tables. And the table I'm talking about, those tables here. No, you have 8 measurements. So you write down 8 here. You write down the regression equation, just like you got in the graph, R square. And then you have to tell me what's the lower and upper bounds of your CL. Sorry. And then we go for this table. This table goes with the first graph. Where's my first graph? My first graph is here. Oh my. Okay, the coefficient is this one here in the regression equation, 20213. 2.0213. Let's see how good this data is. Less than 1% difference. Do you see that? You already did the calculation for you. Okay, you don't have to keep on punching the keys in your calculator. I already programmed everything for you here. And then you fill up the units, the units of the coefficient, the units of the theoretical value, the units of the percentage difference. Because this is a percentage difference, notice that I am multiplying by 100. Okay, what the unit that goes here is just the unit of percentage, okay? That's what you put here, the unit of percentage. Second graph, 8, whatever, right? The equation you have, the R square you got, and then that is the one that you gotta get from your table. We talked about that yesterday. And then the slope. The slope is 4.0269, 4.0269. Do you see how good the data is? 0.04% difference only, right? Okay, and we have a third table, the log table, right in here. Bring it down. So when we are performing this experiment, the first thing that we want to see is the percentage difference, okay, to see if the data is good or not. We're getting good percentage difference right in here. That's the percentage difference. And what about this one? 8 log whatever is whatever, right? R squared is this one. Then from N and R squared, you can obtain the lower and upper bounds of your CL, of their confidence level. You're going right down your slope, and look what the percentage difference we're gonna get. We're gonna get a very small percentage difference, 1.04%. For the sake of this course, anything below 10% is great. Okay. And you're not getting below 10%. You're getting like below 5%. You're getting below 2%. And in certain cases, you're gonna get below less than 1%. And then you gotta write down the units for the experimental, the theoretical, and the percentage difference. The intercept is this one, right? 0.3056. Let's see if it's good or not. Yeah, it's 1% difference. Okay. That's your second priority now. Fill in the table as much as you can. Fill in the tables as much as you can. You can, okay? The next priority is the units. Has to be in the SI units for their combination. In the next, that's what you're gonna do? Sig figs, significant figures. I'm gonna correct all that stuff. I wrote a computer program to do all this correction that you're seeing here. Okay. The only thing I don't have a computer program is to look if you plot the graphs correctly. That's the only thing I don't have yet. But eventually I'm going to do that. I will figure out a way to do that. I still haven't figured out, but eventually I'm gonna do that. But I have a computer program to correct the units. 8 numbers. What are very high? What do you mean are very high? Is close to one, or what do you mean by high? Oh, okay. Yeah. Okay. The types of significant figures I'm gonna talk about that on Monday. Okay, Alisa. We're running out of time. That there's a specific way that I do that, the significant figures. So hang in there until there. Okay. So if I have time, we have 10 more minutes here to go, right? I do not know if I'm gonna have time. But the way I do significant figures. Okay, let's see if I can. So those are 1, 2, 3, 4, right? Those are the main things. Let's see if I can do that right now. Okay. And maybe I already have everything spelled out here. No, I don't. Oh, I have it here. Okay. The way I do significant figures, I do it in the, how do you say? I do that in the conservative way, okay? That's how I do my significant figures. And I tell my students to follow my way because that's how I program my Excel spreadsheets, okay? So here you go. There are two types of significant figures, right? There are two types of significant figures. There are, let's see if we can do that in the next 10 minutes. There are two types of significant figures. Okay, one. Significant figures that are determined from the measurement. Let's have sig figs. Sig figs that are determined from measurements. And sig figs that are determined from the operations that we make, right? The operations that we make in the raw data. And the operations I'm talking about multiplication, division, summation, and subtraction. Okay. Let us start. Okay. Let us start with the significant figure determined from measurements. Okay. Here you go. We have raw data. Remember I told you I have raw data here? The significant figures of this raw data is going to depend on your instrument. If you have a ruler, you will report a given number of significant figures. If you have a vernier caliper, it's going to be a different number of significant figures. If you have a micrometer, it's going to be a different number of significant figures. Okay? In those experiments, what we used here was a meter stick. Okay? To determine L, to measure L, what did we use? We used a meter stick. And it's spelled out right in here. Okay. Ruler meter stick. Both the ruler and the meter stick have a resolution of 1 millimeter, which, by the way, is spelled out like that, 0.001. Okay. In my labs, the significant figures is going to be up to the decimal place of the resolution of the instrument. Okay. I don't use half of the resolution. I don't use half of the smallest division. I use a very conservative way of reporting the significant figures. So if you have a measurement of exactly 1 meter, right? The way you're going to report in your spreadsheet is going to be 1.000000, okay? And I'm going to put it here, meter. And you have, not this one here. And you have to report it accordingly here in your spreadsheet. How do you do that? You have to adjust the decimal places. You have to just adjust the format. You right click in the cell, okay? And by the way, let's do just for one cell and then you do for everything else. Format cells. Excel doesn't have significant figures, but Excel has something else that's very close to significant figures. Excel has decimal places, right? Decimal places is not the same as significant figures, but you can use the decimal places to find out, to display your correct number of significant figures. But you're not going to use scientific in this column, okay? You're going to use number. And because the resolution of your ruler is 1 millimeter, or at the third decimal place, you're going to display 1, 2, 3 decimal places, okay? And it's going to be in the number format. That's how you do it. And you do that for the rest. You do that for the rest. Okay? For the case of time, okay, those are the measurements, right? The measurements go all the way down here. You gotta look at the timepiece, at the resolution of your timepiece. The resolution of the timepiece that my students use is the resolution of the timepiece in their cell phones. If you look at your cell phone, most likely your cell phone has up to the hundredths of a second. The timepiece resolution is going to be 0.01 seconds. And then you display the number of significant figures here accordingly. Right click, format cell, number, 2 decimal places. Okay? 2 decimal places. This one you do the same, this one you do the same. So that's the secret for the number of significant figures for a measurement. The next step is to find out the number of significant figures for those 3 quantities here. Everything that's in red, okay, maybe I didn't record it here. Everything that's in red, you do not need significant figures. Okay? Every quantity in red does not require sig figs. And then you have to use sig figs for the summation, right? Oh, sorry, sig figs here for the summation. First this one, then we worry about this one. We are going to sum T1, T2, T3, whatever number of significant figures you get from this summation, you report it here, right? And then you're going to divide by 3, right? Here, same thing, right? Sometimes, here we have 3 significant figures. Most likely here you're going to have 3 as well. And most likely you're going to have 3 as well. Every now and then, when we sum those 3 numbers, we gain, every now and then, it doesn't happen all the time, we gain 1 significant figure. So most likely this number here is going to have 4 significant figures, most likely, because we're summing quantities, right? And then that's going to be 4, that's going to be 4 as well. 157, okay? So that's what you need to know to start working on the sig figs. Okay, we're running out of time right now. I think I got everything that I wanted. And on Monday, we talk again about this lab report, okay? You don't need to turn in the lab report yet. On Monday, I will tell you what to do. And we move forward with the next experiment. Any questions?
Yeah, Professor, when will our lab report be due?
Well, on Monday, I'll tell you.
On Monday?
Yeah, I'll tell you on Monday. So you still have time. Concentrate on your exam tomorrow, right?
Okay, yeah. And our exam tomorrow is from 12 to 2?
Yes, that's right. 12 to 2, 2 hours.
Okay, thank you.
Okay. So I see you tomorrow.
Thank you.
Welcome.
All right, thank you, Professor.
Welcome. Okay, oh, and feels better. Okay, so I guess I can add my little something there, right? No. No. Tá fazendo? Você tá me procurando? Queria saber sobre o negócio da água dela. Água dela? O Raul tá pagando. Não sei o que, você tá na conta de você tá por dela, também. Ela que me avisou que a gente de água, depois ela ela aliás, recebeu. É, a primeira que quanto tempo? Até com o diálogo, você se entregue. Duas ou três semanas. Não sei. Pode ser que ela achou lá. Talvez ela achou que ela deu um livro. Não falei, não sei, não sei. Vamos conjecturar, não sei. Veio aqui entregar outra. Tem problema dele, não sei. Eu vou colocar aqui no sobre um negócio sobre a água dela. Eu falei que depois da gente você tá. Tá bom.
Deveria ter feito pra você, né?
Docinho. Faz uma banho. Aproveitar a água.
Terminar um negócio que eu tô fazendo hoje de manhã. Se quiser ir primeiro, pode.
E aí, conseguiu uma coisa aí, mano? Depois me fala.
O meu tá. Eu gosto de fechar, né?
Não. E baixar o extrato de novo. Hello, Sumana.
Hi, Professor. I just wanted to ask you about something.
Hmm?
So I'm still not officially enrolled in the class. I'm trying to contact the dean about it, but then they're like out of town right now, so I don't know when I can officially enroll.
Mhm.
So I wanted to ask, like, would it be possible for me to get access to Canvas?
I do not know, okay? I don't have authorization to, I don't even know how to do that, okay? To let you, let me see, did you call Canvas? Did you try to call Canvas to find out?
Call who?
Canvas, you know, they have, oh, wait a minute,